There are tons of machine learning courses online, and honestly, most of what I will teach you in this course can be found out there, scattered across YouTube videos, blog posts, textbooks, and online courses. The information exists. The problem is structure. If you are an engineer or a STEM professional trying to learn machine learning, you will spend a long time piecing things together. You will sit through hours of content that's oriented towards social sciences or computer science or generic data science, and you will keep asking yourself, how does this connect to my work? And that's the gap. This course is designed to close that gap. It gives you a structured engineering-focused path to learn machine learning. The concepts you actually need, in the right order, apply to problems that you can relate to. And when you enroll, you will also get a free written guide that accompanies the course. It covers everything in the lectures and more, so you can always have a reference you can go back to. My name is Dr. Smith, and I'm an engineer and researcher working at the intersection of structural engineering and machine learning. My machine learning story started during my PhD at Princeton. I was studying breakwaters, the coastal engineering structures that protect shorelines from waves. One of the shapes that we analyze is the hyperbolic paraboloid. Predicting its structural behavior requires solving coupled, highly complex partial differential equations. And numerical tools like finite element method gives you answers but not equations. I wanted actual closed form relationship. That's when I discovered symbolic regression, a machine learning technique that can discover equations directly from data. We used it to derive equations for these structures for the first time and published the work in a top journal. That experience showed me that machine learning is not just about classifying images or predicting house prices. It's a tool that can fundamentally advance engineering research. Before you enroll, I want to highlight something very important about how I think about teaching. I see my role here as a tour guide, not as a spoon feeder. I'm going to show you the landscape, point out the important landmarks, warn you about the pitfalls, and give you a map. But you have to walk the path. Most of the things you will truly learn in life, you will learn them by struggling with them yourself. That's where the real learning happens. So think of this course as a guided tour through the essentials of machine learning for engineers and STEM professionals. I'll make sure you don't waste time wandering in circles, and I will make sure you leave with a working toolkit. But the effort, that's yours. I hope you enjoyed the tour. See you inside. So what is AI? Artificial intelligence is a broad field. The term was actually coined back around 1955 by John McCarthy and his colleagues, partly as a marketing term to secure funding for a summer workshop at Dartmouth University. A widely used definition comes from Russell and Norvig. AI is the study of agents that receive information from the environment and perform actions. That's very general. Within AI, machine learning is the subfield where algorithms improve through experience, through data, rather than being explicitly programmed for every scenario. Under machine learning, you've got things like supervised learning, unsupervised learning, and reinforcement learning. And then there's deep learning, which is a subset of machine learning that uses multi-layer neural networks. They are especially good at learning from raw data like images, audio, and text. Now, before machine learning became dominant, early AI relied on something called expert systems, which are hard-coded if-then rules written by human specialists. The key difference is that machine learning models learn patterns from data rather than having a human spell out every rule. Think of it as nested circles. AI is the biggest circle. Inside it sits machine learning, and inside machine learning sits deep learning. So why should you learn AI? There's the obvious answer: demand. Industry and academia are investing heavily. Nvidia is worth trillions largely because of AI hardware. There is arguably a bandwagon effect, and some say there might be an AI bubble. But whether or not valuations of these companies are correct, the practical utility of AI, especially in engineering, is not going away. And that utility is the real reason. Large language models, LLMs such as ChatGPT, can help you code, write, and interact with information in ways nobody imagined 10 years ago. Recommendation systems on Netflix and Amazon personalize what you see based on your behavior. For example, what you should watch next or what you should buy next. But for us, for engineers and STEM in general, AI can classify structural damage from images, predict material properties, write code for us, and assist in design optimization, and even discover equations from data, and much more. In this linear regression section, we predict the stress of a steel specimen from its strain. Simple problem, but it's the vehicle for learning the core machine learning vocabulary. Loss functions, gradient descent, train test split, overfitting, and these are concepts that you will use in every machine learning project for the rest of your career. Welcome back. In this section, we will discuss linear regression, and we will discuss it through an example of predicting elastic stress from strain of a steel specimen. I'll start with the outline. First, we define the problem. So we have the problem setup, which is stress strain of steel. I'll provide you with the data, and this is the data we will be working on. Number two is we will define the linear regression model. Number three, we will define the loss function. I will show you two loss functions in here, the MSE and MAE, even though the application, when we're doing the analysis, we will be just running them on the MSE. After we define the loss function, we can start estimating our parameters. I will introduce two ways for the linear regression model to calculate or estimate the parameters. First is the closed form solution, and number two is the gradient descent. The first method, by the way, is sort of like I don't want to say specific to linear regression, but it works when you have a very simple loss function, and very loss function due to the fact that you have a very simple model. And in here it's the linear model. The other method is way more general, gradient descent, and this will be sort of your friend throughout your machine learning investigation. So this is a method that keeps recurring, and we use it in machine learning in almost most of the machine learning applications. After we estimate the parameters, we will discuss generalization and extrapolation, and finally we will talk about overfitting. I want to stress something very important. If these steps don't make sense to you right now and why we have them in this order, that's okay. But they will keep recurring over and over again. You define your problem first, then you establish your model, what model you're trying to fit, and then you define your loss function, and then you do a parameters estimation, and then you see how your model generalizes. So all of these concepts, I will discuss them, and they will be easy, by the way. If you study this course from an angle that talks about social sciences or something that's not engineering oriented, they will be a little bit ambiguous, but because you have the engineering background, you will tend to understand them here very well from an engineering perspective. So all of these concepts in here, they will occur over and over again. The problem goes as follows. We have a steel specimen in here, the one you see in gray, and I'm applying an increasing load P, tensile load of value P, and this load is varying, so we keep tensioning the specimen, and while we're applying the load, we measure the deformation. So our deformation would be delta L. Okay, so you can see as we increase P, delta L will increase. And from these measurements, if we have the original area, let's say we have the original area, and we call it A0, if we divide P by A0, we get the stress, right? This is the applied stress or the engineering stress, because we're dividing by a constant area, which is the original area. And if we have also the original length and we're measuring how much it's changing, then we can get, by dividing delta L or over L0, we get the strain. You might be familiar with these concepts, but it's important to understand that what could be the input, what could be the output in this case. So we have the stress and strain. We can measure them from the load and from the deformations that we're measuring. So we can collect some data. In here, I have 10 data points, so you can see the ones in blue. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are 10 data points where we have the strain on the x-axis and the stress on the y-axis. In our example here, this is a synthetic data. So I created this data, and I will show you how I did them after we're done with all of the lecture slides here for the concepts. So make sure we understand the concepts and the derivation. But after I'm done with these series of slides, I will show you the code, how I generated the data and how I ran the analysis and all of this after we're done with the concept, with understanding the concepts. So we have 10 synthetic data points here, and each one of them is a pair of stress and strain. Our goal is to predict the stress at unmeasured strains. So what do I mean by that? For the measured points, like let's say this point and this point, we can already we know the values of the stress and the strain, right? So if I give you a strain, you already know the value of the stress in here because that's the data that we collected. However, if I tell you what's the value of the stress at this specific amount of strain, then obviously you can guess you need to do some sort of interpolation to be able to get what's the stress value at that specific strain, correct? And that's the goal, sort of the general goal of machine learning. You're given some data and you're trying to teach the computer, and here a model, we call it machine learning models, and you're trying to teach them to understand the trend and the pattern of the data to be able to make some inference. So the goal in here is to do some sort of interpolation to be able to predict the stress at values of strains that are not in the data that was supplied to you. And again, the data in here is synthetic, but the same concept would apply if you were having experimental data that you collected as well. Another goal that we might be asking in here is to estimate the elastic modulus from the data. But this is sort of secondary to the main goal, where the main goal is to be able to predict the stress at unmeasured strains. So the question becomes, what is the best model that we can fit in here? Under Hooke's law, we know that stress is proportional to the strain. So the stress is sigma in here, and the strain is epsilon. So this is strain, this is stress, and they're related through the modulus of elasticity, E. And the point is, this is the underlying physical model, right? We know this is the real model if we have an elastic material, so we don't have any nonlinearities in here. However, in practice, the measurements include noise. So if you were going to do a physical experiment, you will get some noise. However, in here, I tried to mimic this noise by introducing, like synthetically introducing some noise. And I will show you, by the way, after we're done with this series of slides, I will go over the code, how I generated this figure, how I generated the data, how I ran the analysis, and all of this. Since we have noise, you can guess that a single line, if we pass a single line, because the underlying physical model is just a straight line that passes through the origin, correct? However, since we have noise, we cannot have a single line that passes throughout all of the points. We cannot do that. So any line that we draw, and by saying, why did I introduce a line? Why I'm trying to fit a line? I'm trying to fit a line because I know in this case that the underlying physical model is a line, okay? So we start, and the underline is sort of the simplest model we can start with. So when I'm trying to fit a line, I cannot let it, again, pass through all of the points at once, which means any arbitrary line I will have some sort of error with respect to the observed data or the ground truth data. So this terminology that I just said, ground truth, is the observed data that you have. And you can guess, you're telling me, it's like, why do I call it ground truth, even though I know it has some error from like the actual physical model or from the actual theoretical model in this case? The reason is because it's called ground truth with respect to the machine learning model you're trying to fit, okay? So your machine learning model, generally the best thing it can get is your data, the data that you collect, okay? And that's why it's very important to collect good data. So let's try to introduce something called a residual. We can do that by first drawing an arbitrary line. So you can look here at this arbitrary line. This is not the best fit line. This is just an arbitrary line for now. Consider this observed this point, this observed stress. So this is a stress and strain value. At this specific stress value, or at this specific strain value, we have this stress, right? However, the line, this arbitrary line, will make a prediction at here, at this value. So let's define the residual in here. If we call this point point number 1, and this is point number 2, etc., then the vertical distance in here, like we said, is going to be R2. This is residual number 2 of data point number 2. This is going to be equal to sigma 2. Sigma 2 is the observed data at the second index. So this is the point here. This is the value of the stress in here, minus the predicted. So sigma hat, when I say hat, usually in machine learning, we mean by predicted. The predictive value of the stress at point, the second point. So this is at epsilon 2 at the strain value of index 2. Okay, so this value is sort of the error at each point we're going to have, the vertical distance. This is the error we're going to have from the model that we're fitting. And we wrote here the residual for one point, but we can write it for any point of ith index, correct? So if we write the residual for all of the points, can you take a guess what we're trying to do here? Like if I write all of the residuals, I'm trying to get a model. The model that can best fit the data is the model that reduces these residuals in this case, correct? But how do we define the error? And this is where we get introduced to the new concept called the loss function. So in machine learning, we sort of quantify the error we have with something called the loss function. Before I show you the loss function, I just want to make sure you understand the linear model we have in here. When I'm assuming there is a linear model, like the arbitrary line that I showed you, any arbitrary line I'm going to draw has an equation. The equation of a line simply is y equal ax plus b, correct? So this is the equation of a line. But I'm saying I'm trying to predict the stress. So my y would be sigma predicted at a certain value epsilon. So this is a function of epsilon of a strain. And my a, this would be the slope, correct? In machine learning, we don't call slope and intercept. And generally, when we talk about a model and its parameters, so this is a parameter of the model, right? This is what defines the model weight we have. So we define them as something called weights or parameters of the model. So we're going to call this one W1, okay? And then my strain, this is just simply epsilon. And B, we call W0, okay? W sub 0. So this is the model that I have. I just want to make sure that you understand this. So a linear model has two parameters, the slope and the intercept. But in machine learning, we just call them weights, okay? So the weights, we have W0, that's the first weight, and W1, okay? W1, as you can guess, is the slope, but from the Hooke's law, you can guess that this is the estimate of the modulus of elasticity. The second parameter is W0. Ideally, this is equal to 0 if the points fit exactly on Hooke's law, where the line just passes through the origin, so we don't have an intercept. But in here, when we're running the machine learning analysis, we let it change freely, and then we will find what's the value because it captures any sort of measurement offsets that we have. So like I said, it's very important in machine learning terminology to understand that W0 and W1, etc. Like we could have machine learning models, and here we just have two, but we could have billions of parameters in a model, and you could see how things can get really complex. But it's very important to understand that we call them model parameters, and the whole goal of machine learning is usually to estimate these parameters. But before, remember, we define the model first. You get your data, then you define your model, and then we estimate these parameters that best fit the data, that best help the model fit the data. Now we can go into more details about the loss function. So a loss function, and like I said before, we're trying to find the parameters that help the model. In this case, we have a linear model that best fit the data. In here, a loss function is defined as a function that maps the model parameters. In here, in our case, the model parameters are what? Are W0 and W1. So it maps the model parameters to a single scalar measuring the overall misfit. So measuring the overall misfit of the model, or the error, some sort of total error of the model. I will introduce two loss functions, mean squared error and mean absolute error. So MSE and MAE. The most commonly used one is MSE, but I will also show you MAE, and you will see where we use, like when do we use this or when do we use that. But again, most of the time we use MSE or actually a combination of both of them, okay? And we're going to stick to the terminology of saying loss function in machine learning. You can call it error, but in machine learning terminology, we just call it loss. So the loss function is a function, like I said, that maps the model parameters. So it takes the model parameters, not the data points, and these are sort of the ones varying, the model parameters, we're trying to vary them. So they are the sort of the inputs to this loss function, or the parameters of this loss function. So MSE is defined as follows. So this equation. So what is this equation exactly? This equation is simply we're summing the residuals. So if you look at the ones inside, we're taking the square off. This is simply the residual I of subscript I, right? Because remember, the residual, we said it's the difference between the measured data, right? This is the observed data, the ground truth, minus the predicted value of the stress at epsilon I, sub I. And we were trying to fit a linear model, which means it's sigma I minus the linear model, which is W1, epsilon I, plus W0. Okay, so this is the residual at point of index I. And we sum over all of them, over all of the indices. So we have I equal 1. We start from I equal 1. This is the first data point. And then we go all the way to n. In this case, in here, n was the total number of data points, for example. In the previous slide, we had n equal to 10. We had 10 data points, let's say. Okay, this will vary. There is way more nuances into this. So we'll talk about it later. That n is usually in machine learning, not the total number of data points. But we'll talk about this later. So what we're doing here in MSE, we're taking the residual, each residual, taking the square, summing all of them, and dividing by n. Okay? On the other hand, for MAE, we're not taking the square. The residual is here inside, but we're taking its absolute value. Okay? And you could see if you have a residual, a certain value of residual R, we're squaring it. So we're saying the loss is bigger, okay? And always think of the loss as an error, okay? So the loss is sort of how much loss you incur. That's hence the name. So the bigger the loss, the bigger the residual, you're gonna square it. So it's gonna have a bigger impact on your loss, which means the MSE penalizes large residuals more strongly because we're squaring the residual. So which means it's sensitive to the outlier. So if you have a prediction of, let's say, like 30 megapascal, and you predicted, let's say, the error, like the current model that you have predicted 50 megapascal, then your residual is squared. For this case, R squared would be 20 squared. So it's a big value, right? So we're squaring the residual. For the MSE, MAE does not do that, does not square the residual. It just takes the residual and their absolute values. We like to use, by the way, the MSE because it's differentiable. So the square, the quadratic function is differentiable. So we like to use it. And it's usually the most commonly used one in machine learning. So we're going to use it in here. Now that we have the loss function, and we're talking about the MSE, like I said, and we have it in a very simple form, okay? Like, don't be intimidated by the form right now because it's a sum and all of that. But if you look at it like closely, you will notice that JMSE, the loss, is simply a function of W0 and W1, okay? So everything inside is sort of like constants. You have a lot of constants, and the only variables you have is W1 and W0. So don't be intimidated by the form. But right now we have a nice form of the loss function, and you could see that we were able to write the loss function in a really nice way because the model we're trying to fit is an easy model, is a linear model, okay? So now that we have the loss function written in a nice way, we can simply take its derivative, correct? Like if I tell you f of x equal x squared, and I tell you what's the point that this value or this function achieves the minimum, you're going to tell me, it's like, okay, we can take f prime of x and set it to 0, which means 2x is equal to 0, x is equal to 0, correct? This would be the case. So if we have a sort of like a very easy function to calculate, which is the case here, by the way, for the loss function, we can just take its derivative and set it to 0. And why I'm doing this, once I do that, and I take the derivative of the loss function, so del j, by the way, del means just the partial derivative, because in here we have two parameters, okay, into this function, w0 and w1. So when you take the derivative, you say del, not d, okay? If you have a just single variate, you would just say d. Anyways, so we take del j by del w0, and we set it to 0, and we also take del j by del w1, and we set it to 0. And then we can solve for what? For the parameters. Just like in here, we're solving for x, the one that minimizes the function in here. Okay, we could do the same thing and find the parameters that minimizes what? That minimize the loss, which means these are the parameters that we can calculate using like a closed form solution in here that minimize the loss function, and which means it minimizes the error. Okay, and that would be the parameters. This would be the slope, and this would be your intercept of the best fit model. Okay, and here on this page, I'm showing the closed form solution. So in here, you could see that I wrote them explicitly, and you could check that for yourself. Okay. I want to just stress here, by the way, the epsilon with bar, this is just the average value of the epsilons. So this one would be, you can get it from 1 over n from I equal 1 to big N of epsilon. So this is just the average value. Whenever you see a bar, we usually say it's just the average value. And the same thing in here. This is 1 over n of sum of sigma I, okay, from I equal 1 to n. Okay, you can check that for yourself. The point is, I just want to show you, you don't need to derive that yourself. It's a fun exercise to do that. But the point is to show that because we have a very simple loss function in here, we were able to calculate the parameters. I have, by the way, the Python, like the programming language implementation for this example, and I will show you again after we're done with the slides. If you run the analysis and you calculate this value, you will find the W1 to be equal, again, this is sort of the measurement of the youngest modulus, to be equal to 1.97 times 10 to power 5 megapascal. And also the intercept is equal to 5.3. See, it wasn't 0. It's very close to 0 though. 5.3 megapascal. If I told you that the estimate, the one that was given to you by the manufacturer of this T specimen, it was 210 gigapascal, and then this value sort of will be around 94% of the manufacturer's specified value. Okay, so you can make your data supplied, for example, when you have a data and when we're doing either synthetic data or simulation data or even experimental data, they could tell you a lot of information about a certain specimen or about the underlying sort of physical model. And this will be important actually in the next section, and we'll talk about it in the symbolic regression analysis. So like I said, this way only works, though the reason we were able to easily derive it and just set the loss function equal to 0, the derivative of the loss function equal to 0 for both parameters, is because we have a very simple model, a linear model. Okay, so this only works when we have a linear model in parameters. So this is linear in the parameters, and the loss function is quadratic. We were easily able to set it to 0. However, in practice, we might have billions of parameters, okay? So we don't just have 2 parameters. We have billions of parameters, and the loss is not usually that easy to determine because the underlying sort of model, or the model we're trying to fit, is not simply a linear model. Hence, we need to introduce sort of the most important optimization method in machine learning, which is gradient descent. And trust me, you might be familiar with most of the concept, but in here we're just trying to apply it in machine learning context. So when the loss function is sort of complex because of the fact that in most machine learning analysis, you will be trying to fit a model that's not just simply a line. Usually you will maybe you will try to fit like neural networks, and they have hundreds of thousands, millions, or even billions of parameters. So we need a general way to estimate our parameters, okay? And I like the linear regression. It might be something very simple. We're all familiar with it, doing linear regression. But it's actually a machine learning. It's fitting a model, whether it's a line or something with billions of parameters. It's still machine learning. You're trying to fit a line or a model and to fit your data to make predictions or make inferences. So the general way usually we do it to find sort of estimate the parameters, the optimization method is called a gradient descent. And this applies when we have a line. You could do it when we have lines or when we have models of billions of parameters. So gradient descent, it has 2 things. It has gradient, the gradient, sort of the derivative, and then descent, sort of going against a gradient. So we descend against the gradient direction. And you can guess, previously we calculated the parameters directly using a closed form solution. In here, since we can't, or we're assuming in complex settings we cannot, we try to do it iteratively. So we do iterations to arrive at the value, or the parameter's value that minimize the loss function. So let's say we have a certain parameter called x, okay? And x, in our case, for example, just so that we understand the analogy of what's going on, like what's a function of what exactly. Your x in here, x would be like, for example, w0 and w1. Again, I'll repeat, and this concept might be confusing in the beginning, but that's okay. So w0 and w1, they are your parameters. So you're trying to change them, okay, until you minimize your loss function. So the loss function is a function of these parameters, okay? So let's say you have an x, a parameter called x, okay? And again, in this context, x could be either w0 or w1, okay? So if you have a parameter, to minimize the function, let's say you have a function f of x, okay? So your input is x. Again, in here the analogy is we have w0 and w1, that's your x. And f is your j, is the loss function, okay? So if we have a function and we're trying to minimize it, what do we do? Let's say we start at a value, a certain value, xk, okay? So this is at certain time step k, like right now where I am. And I will show you the example on the right in a bit. But let's say I start a certain value, xk, and I'm trying to move in a direction that minimize the function f. So let me give you an example. So let's say we have a function f of x, okay? And this is a function of x, and it looks something like this. And let's say this is point x sub k. So this is the point where I am right now. So we're going to change it. We're going to iterate to reduce the function. In which direction? Can you guess in which direction I have to move in order to minimize the function? At this point, I have to move to what? To the right, correct? So I have to move in this direction, to the right. However, if you calculate the derivative at this point, you will notice that the derivative points to the left, correct? Not to the right, which means I have to move against the gradient in order to reduce my function. So this is the whole idea, by the way. When you have a function and you're trying to minimize it, you move against the gradient, okay? This applies whether you have one parameter, like let's say just x and f of x, or when you have billions of parameters. You try you would derive your function with respect to that parameter, and you just go against the gradient. The question is, when I say I move against the gradient, like in the direction against the gradient minus the gradient, the question becomes how much of the gradient, how much I move. Do I move 2 times the gradient, 3 times the gradient, or a small value of the gradient? And it turns out this how much is what we call the learning rate, and it's a hyperparameter. What do I mean by hyperparameter? This is another thing that we need to understand. A hyperparameter is something that you choose when you're running your machine learning algorithm. Usually it's user chosen, okay? So you choose it before you start, generally speaking, okay? So a hyperparameter, you choose how much when you're trying to do the iteration, and here what we call a learning rate, when we're running the algorithm. So this learning rate is what we call in here eta. So eta is your learning rate. So again, if I have a certain point, xk, the next point I should go to is the current point minus, or I need to move against the gradient. The gradient in here is f prime of xk, so that gradient or the derivative at that point. And how much I'm moving sort of in that direction, the amount I'm moving in that direction is sort of multiplied, or the step is multiplied by by eta. So this sort of will tell me how much the absolute value of the step size, eta times f prime of x, k, is the absolute value of the step size I'm moving, okay? So I move against the gradient. So as you can guess, eta is a positive number, okay, because we have here a negative. We're already taking care of the fact that we're moving against the gradient. So eta is a negative, is a positive number, and again, it's a hyperparameter. You chose it. You can choose it. And when I'm moving against the gradient, or in the direction negative to the gradient, we're moving technically downhill, right? So if we start here, we're gonna go here, and this will be, for example, your xk plus 1, and we can keep going until sort of the slope flattens, okay, or until your derivative is very close to 0, or whatever termination criteria we will talk about. We'll talk about all of this. When do we stop? Okay, we generally want to stop at the sort of the lowest point we can get. So I'll repeat again. Your w0 and w1 are what we call parameters. Okay, because they are the ones you're trying to estimate when you're running the machine learning algorithm, which is the gradient descent in here. And eta, or other things that we choose usually, they're called hyperparameters. So we choose them before we start running the analysis. I want to highlight the importance of choosing the step size, eta. If your eta, I'll first start with the just highlighting the eta again. So let's say you have x0. This is like x at step 0. This is when we started. This is when we initialized. So by the way, whenever you start running your machine learning model, we're gonna initialize, like usually by random values. We assign random values to these parameters, and then we start running the algorithm to descend against the gradient in the negative direction of the gradient. I will show you the implementation in the code, and here we're just trying to understand the concept. So let's say in here we have x0. This is the point we're starting at, and then x star is the global minimum, the lowest point we should sort of try to go closest to. We move against the gradient, so this is minus eta f prime of x0 at this point. Now the question is, how does choosing eta sort of impact the learning algorithm? If you choose your learning rate too large, like you start here and you choose your eta too big, yes, you're moving against the gradient, but you might end up jumping too much to the other side, okay, to the other side of the function. So you keep sort of oscillating, and you're not sure we're going to converge to that x0, the nice point that we're trying to go to. However, also, if your step size is too small, if you choose your eta to be too tiny, then most likely you will move, yes, against the gradient, but you will make very small steps, and then it will take you forever to be able to go to x0. Okay, so what we want is a reasonable step size. Okay, a reasonable step size will sort of decrease your function. Okay, but it will do it in a reasonable way, not too slow and not too fast. Or if it's too fast, then you might end up oscillating. Like I said, I will show you the code, exactly the implementation of gradient descent. But in here, I will show you the results, exactly what we were doing. If we start W0, this is this was the bias term, the intercept. If we set it to 0, we start from 0. It doesn't mean it will always be 0. We just start with 0. And then W1, we start with 50 megapascal, let's say. And the learning rate is equal to 0.5. And we run the iteration 5,000 steps. Okay, so we go 5,000 steps. And if we do that, and we do the loss function, so let's go with the step. I showed you the sort of the derivative of a function, and we take the gradient, we go against the gradient. But in the case of the loss function, this is how it would look like. So we start with a certain W0, and then we need to update it. How do we update it? We update it by W0. This is W0, so we take the original value, minus the gradient, right, times the learning rate. So this is the gradient, del j by del W0, okay? And then for W1, the same thing. We update it, and the new value would be W1 minus eta del j by del W1. Now, the nice thing is we're calculating the gradient in here, okay? But something you need to understand that I will go in more details again in the code is that the functions that we're usually defining, whether they're simple lines or even when they're neural networks with billions of parameters, usually a lot of them are already embedded in these libraries. So when you're trying to calculate the derivative, it's so easy to calculate the derivative. They already do it and sort of internally, so you don't need to worry about doing it. As long as you define your function in these libraries, they will be able to calculate the gradient for you with respect to these parameters, okay? So when we calculate, we can calculate the derivative with respect to W0 and with respect to W1. And if we run these iterations, we'll find that W1 is equal to 1964.9 megapascal, and W0 is equal 5.45, which is very close to the values that we obtained from the closed form solution. And by the way, this is the best fit model that we obtained from these parameters. This is the closed form solution, but it's almost the same for the gradient descent. So you could see how it fits like in between the points in here. So this line, because we obtained it through the optimization steps by minimizing the function or the loss function with respect to these, with respect to the parameters of the model, W0 and W1, this model will be the best fit throughout the data, and this is expected. Remember when I defined the loss function with respect to these parameters, and I said we start iterating in the gradient descent, right? If we go back here, when I said we start iterating and we run them for a certain number of steps, and here 5,000 iterations. So when we're running the iterations, we're going against the gradient, which means we're descending. So if you keep measuring the loss function, if everything is fine, okay, if the step size is reasonable, then your function, the loss function in here, J, MSE, the mean square error, over iterations, the more you run it, The longer you run it, the more it's going to decrease, okay? And then it plateaus when sort of it reaches the minimum, okay? This plot is what we call usually a machine learning loss curve, and it's very important, very, very important to monitor this curve to make sure when you're trying to fit something, when you're doing machine learning, you want to make sure that your curve is sort of healthy and it's decreasing in a nice way. Another thing I want to talk about here, which we'll later talk also about in neural network section, is stochastic gradient descent. So what is that? Stochastic means sort of random. Gradient descent is what we just discussed. When we're trying to descend, I want to show you here, we summed over n, and we said n is equal to 10, for example, in this case. So it's just a few data points. That's not a problem. We can easily sum over them. However, imagine you have so many data points, and it becomes way more complex to calculate your loss function and its derivative and sum over all of them over all of these points, correct? So what we usually do is, instead of using all of the data points when we're trying to iterate, we use a batch of these data points. So we use a random mini batch per step. So we don't calculate the loss function over all of them. This means that we have a cheaper update, and it scales very nicely when we have a huge data set. Not just 10 in here, we have just 10, but when you have thousands and millions of data points, it becomes way more efficient to do that. Now I want to discuss one of the most important concepts in machine learning, which is generalization. So what is generalization? Generalization is the performance on new unseen samples from the same distribution, or we call it here in distribution. So what do I mean by that? First, I want to define multiple things. Interpolation. If I have 2 points in here, okay, and I tell you do some prediction in between, like let's say I want to make a prediction of a data point in here, you can simply tell me, so, okay, I will just fit a line in here, and then you can interpolate. So you're interpolating between these 2 points, and you can make a sort of a prediction about any of the points between these two points. So this is what we call interpolation. So it's in between the points that you're trying for just 2D in here. I'm defining for just 2D. So you can make any prediction between the 2 points along a line. Okay. You don't need necessarily to fit a line. You could fit something else. But the point is, you'll make a prediction. You will be comfortable making prediction between these 2 points, right? Especially if these 2 points are representative, sort of like they're nicely spaced between each other. But anyways, the concept is you make prediction. Interpolation is you making predictions within the observed data range in this concept. Okay, so within our data points that we had, we can make predictions. And like I said, we have higher confidence when we're trying to do that. However, if I'm trying to tell you we're trying to do extrapolation, let's say I want to tell you, it's like, oh, what's the point in here? Like, what's the prediction? What would be the y value at this point x? Okay, the one I'm putting a circle. So what would be the value here? You will be way less confident about the line in here. Like, you don't know, should you continue it and you make extrapolation here? What if the behavior change? What if it's no longer a line? What if the underlying physical model, if it's a physical problem, what if the underlying model changes? So these questions, keep thinking about them. And this is where out of distribution becomes important. So there are test conditions, like data you have not seen or the model haven't seen, where they differ meaningfully from the training. So what do I mean by that? Usually this concept is a little bit like more abstract, but it's so nice that it relates to what we're doing, which is the steel specimen. And actually, this is why I chose the steel specimen example, because it makes it easy to understand generalization. So what do I mean by that? Remember when I showed you the data points of the steel examples? I made sure that the data is actually within the elastic range. Okay, so I made sure all of the data is within the elastic range when I showed you these data. So they follow a linear behavior. There's some error or some noise, but they follow a linear model. So when we try to fit a model in here, a line, this line, if you try to make a prediction along this line, along this range to the elastic range, it's good. You're confident in your prediction generally. However, if I try to tell you I want to make a prediction outside that data range that I gave you, the elastic regime that you trained on, that you trained your model on, then you will be way less confident. And you should be. The reason is because beyond this range, beyond the elastic range, okay, and again here we're putting the condition elastic in elastic, but this concept is general. when you go beyond the training range, you become less confident in your prediction. And in here, this makes a perfect example, because above the range that sort of we trained on, the behavior of your model will change. It will no longer be a line. It will follow this curve, this shape. Okay, and this is the failure sort of curve at the end. Your steel will fail in here, for example. So if you try to make a prediction in this range, let's say you predict this value, then obviously this is wrong, because your actual value will be somewhere in here. So this is your error, because you tried to predict something out of the distribution. It's a completely different behavior, and you made a prediction with a linear model, with a model that does not apply in that behavior. So it's very, very important to have a model that generalizes well, at least within your training range. And this is what we usually mean by generalization. At least within the training range, you're trying to make the model sort of have good performance. So how do we validate generalization? How do we make sure that we're achieving it? Let's say I give you a certain number of data points. Let's say 100 data points. Okay, you should not, and I hope it makes sense. You should not take this 100 data points and train your model on. Okay, like measure the loss function, take the derivative, do the iteration. You should not show your model. When I mean show, like you train the model on them. You should not show the model all of these 100 data points. Instead, what you should do, for example, this is one method. You can take, let's say, 80% of them. So this is 80 points. Okay, so this is 80 points. And then you can train the model on them. Okay, and for the remaining 20 points, these are the held out data set. Okay, so this is 20 points in this case. Okay, you can see the performance, you can test the performance of the model that you got from the training data that you trained on the training data. You can see the performance of the model on the held out data set. Okay, if the performance on the testing data set is good, then you made sure sort of that your model generalizes well. Okay, and it's very important that this test set is something that the model has not seen before. So what we're trying to do is we're trying to make sure that our model does not memorize the data. You're telling me, it's like, but what do you mean memorize? It's just a line. Yes, of course. In here, it's just a line. It's like it's gonna fit nicely. Like it doesn't have much capacity sort of to memorize your data. So what do I mean by memorize your data? Let's say I have a different model I'm trying to fit. Okay, so this is the model I'm having in here. Okay, this is the same data points, by the way. The one I have in blue and red, this is the same data point. The blue data points are the ones I use for training. So I show the model and I'm trying to let the model fit them. However, let's say I have a model, not just a straight line, but segments. Okay, I'm trying to make this is a new model I'm trying to fit. Okay, so let's say I try to fit a model that has segments, linear segments, instead of just a single line. And I tell you, this line could fit the training data, the blue ones, perfectly. Like, look how nice this is. It can fit them perfectly. Okay, so each point it sees, it creates a new linear segment and it connects to it. What is your residual in this case for each point, for the training point? It's going to be 0, correct? Because Ri, okay, is your sigma I minus sigma hat of epsilon I. And both are equal in here because you're memorizing them. You're fitting them exactly. So your residual will be 0 and your training loss will be 0, correct? Okay, your MSE, your mean square error. However, does it mean my model is doing well? You could tell that it's not doing well. Why? Because it memorized your data. You showed data and it's memorizing, which means it's not sort of understanding the physical model. Okay, it's just memorizing data. It's not understanding the physical trend, the overall trend. It's not generalizing well. Why? It's because when I try to test it on the held out data, let's say these red points, you will see it will have a huge error on the testing data. Okay, so the training loss is equal to 0 here, but testing loss is very high. Okay, and this means if you see this trend, if you see your training loss is sort of low, and then your testing loss is very high, it means your model was memorizing the data. Usually this happens when your model is more and more complex. We didn't have it for a single line when you had a single line because the line is sort of doesn't have high capacity to memorize the data. But if you have a model like in here, a segmental, like n segmental or n minus 1 segmental model, linear segment model, this one has higher capacity to be able to memorize your data. So we want a model that generalizes well, that make good prediction on the testing data that it has not seen during the training, okay? And this brings the concept of Occam's razor, and this is something that you will hear a lot in machine learning. So among models with similar performance, prefer the simpler one, okay? So on here, you could see that this one performs very well, okay, or relatively very well on the training, okay? It's in here, the loss is 0. But also the linear model, the one when we fit, it also performs very well. And here, because this one has a higher capacity to fit, you should go and prefer the smaller model. This is a general concept. We will talk about, there is more, again, more nuance when it comes to neural networks and like more complex models. But generally, when we have models with similar performance, we should go with the one that is simpler. So what are the key takeaways of these slides, the conceptual slides, and then again we will go with the codes, with the script. A loss function quantifies the prediction error, okay? And here we use MSE. Usually it's the default for regression problems. Gradient descent iteratively minimizes the loss. And this is more general. This is the most general optimization way in machine learning. The learning rate is a critical hyperparameter, okay? So it's usually user chosen, even though we can change it using something called schedule, and we'll talk about it later in neural networks. If the learning rate is too large, we might have oscillation and even divergence. We will not converge to that minimum point. And if it's too small, we will have very slow convergence. In machine learning, generalization is the ultimate goal. We want to make sure that we have good performance on the held out data, which the model did not see during training. Finally, overfitting. We memorize the data, and usually because the data has noise, has some sort of like noise from the physical, with respect to the theoretical model, then we might have fitting of the noise. If your model has high capacity, like the segments you saw, it will fit all of the points, which means it's literally fitting the noise that we have. And that's why we tend to prefer simpler models when the performance is sort of comparable. I mentioned in the course prerequisites that Python knowledge is optional, and I intend to keep that promise. Python or any other programming language is a skill that improves primarily through practice, but developing programming proficiency is not the primary goal of this course. I will show you a Python implementation of linear regression. However, I will not go through the code line by line because the level of detail is unlikely to be helpful in this context. Instead, I will focus on the overall structure of the main ideas. You can review the code yourself if you're interested in the implementation details. Fortunately, there are now AI tools that can assist with writing code and even running the scripts. Later in the course, I will demonstrate how you can use these tools to support your workflow. Remember that your primary role is an engineer, not a programmer. The goal is to understand the concepts at a high level and apply the appropriate tools when needed. That said, of course, developing programming skills is certainly beneficial and can make using these tools easier. The script that I will run right now, you can find it in the resources section in the beginning of the course, or you can follow in here, and I will show you two ways to download that script and to how to run it. When you are running scripts, you can run them either locally on your computer, or you can run them on the cloud. In here, I'll show you how to run them on the cloud. Specifically, we will be using Google Colab. Google Colab is a platform where you can run these scripts, like Python specifically in this case. And I think it's very important to introduce you a little bit to GitHub. If you're familiar with it, that's okay. But if you've never heard of GitHub, GitHub is sort of like Instagram and Facebook, but for your scripts. So let's say you want to publish a paper, you can publish a paper and put it in a certain journal, but the script or the codes that you use to generate your data and do the analysis and get the results, you can host them, you can place them on GitHub. And the nice thing about GitHub is you can have a version control. So for example, if you're writing a code and you updated it, and let's say later on you want to go back to a previous versions of that of your code, you can just roll back. For example, this is my GitHub. like I have a bunch of projects in here. Like each one of them, by the way, they were for different papers that I published. And you will find the link for my GitHub in the description of this lecture, and also in the resources. And by the way, this is the GitHub project. This is sort of the folder where I placed the scripts for the course that we're doing right now. You can click on it in here and open it. And these are the scripts you see in here. So this is chapter 2, linear regression, and chapter 3, symbolic regression, and chapter 4, neural networks. So there are two ways we're gonna run it in Google Colab, like I mentioned, these scripts, okay? And by the way, IPYNB. This is Jupyter Notebooks. This is interactive Python Jupyter Notebooks, okay? You can see here the extension. This is Python, but you can run the Python in cells, in different cells, not a single folder. So you can select and run cells that you're interested in, and you can put also markdown. And these markdown, they will like nice text where you could say like what each cell represent and headings and all of this. So it's really interactive Python code. Like I said, there are two ways to access the code and run them on Google Colab. So either we can go here into under code and then click download zip folder. So you can download the zip folder and then extract it on your computer, and then we upload it to Google Colab. This is one way, so we could do that. Or I like the other way, which is directly from Google Colab. So Google Colab, like I said, it helps you run Jupyter Notebook, this kind of files directly on the cloud. So let's say your computer is not that sort of powerful to run certain scripts, and this will be important later when we're training neural networks. So if your computer is not powerful, or if you want to run multiple scripts at the same time, it would be way better to run it on the cloud. For the cloud compute, you can either have like a free version, which is more than what we need in here, or you can have subscription, but you don't need that for this course. To get started, you can just search Google Colab in here on Google or anywhere, and then you can click here on Google Colab, the first thing you see. Now, of course, you will have to have an account, a Google account, to be able to access this. So you can create an account, and then to open your notebook, you can create a new notebook, by the way, from scratch. We can write everything from scratch, or we can upload it here. So if you already downloaded it, you can just upload your file that you're interested to run in here, or we can just directly go to GitHub in here. This is some of the options that we can open. So we can go to GitHub, and you can put the GitHub URL, the link to certain profile. So in here, for example, I can put my profile, HSE95, and we click search, and then you could find all of these projects that I created, okay? So I'm gonna go to the ones AI for Engineers guide in here, and then you will be able to find these files that I created, okay? We're going with chapter 2, linear regression, so we can open it in here. Now that Google Colab opened, you can see that there are multiple sort of types of cells that we can have. Like this thing I'm right now hovering over, I can double click it, and you could see that this is sort of like a Word document or even a nice formatting where you can write whatever you want. And this is not part of the script. This is not a cell that has a script. So you could just write whatever you want. For example, one hashtag, and you can write something. This means it's a big heading like this. A regular text, it will just be displayed as a regular text. To bold something, you can put double stars in here, and so on. So it's really nice formatting for to be interactive. So if you have a client, you could show them the cell, like this Python Jupyter Notebook, or if you have like a presentation research, it would be really nice to show this to your team. So as you can see, this is, like I said, just a markdown where you could write whatever you want. And in here, this is the actual Python code. So in here, it just runs a Python code. To run the code, we can either here click run all, and it will run all of the cells. Like I said, it will run the cells that have codes in them. This code, okay? This one is just the one on the top in here. It's just a markdown, okay? So it's not, it doesn't get treated as a code. So only here the ones that are in actual cells. And if you're asking me how to add that, I can go a little bit under the cell, and you could see I can add either a code cell where I can put the Python code, or I can add a text. And this is just a markdown like these titles and the text that we have. So let me try to run cell by cell. So instead of running all of the cells, and again, you should go over the code, and I will show you at the end like how you can generate the code with AI, with ChatGPT and other tools like Claude, and how to run them with these tools as well. But for now, we'll run the cells one by one. So for example, in here, we just need to import libraries that help us perform the analysis. So I can click run here, and then it's going to give me a warning that I got the code from like external sources. In here, it's GitHub. So I can click just run anyway. But of course, you should run codes that you trust. So run anyway. So it already ran. It's just importing libraries. After I import the libraries that I need, I will generate 10 measurements, like the synthetic data points that I told you about earlier. So this is how I generated them. So I assumed a certain modulus of elasticity. I generated the strain range that I'm interested in, and I made sure it's within the elastic range. We talked about this. And then I convert it to the percentage. When I'm plotting, it's nicer to plot in percentage. And in here, this is sort of the fake noise, the artificial noise that I introduced to calculate when like to the stress values that I calculated. So this is how we get the stress. Again, it's just certain the actual linear behavior plus a certain noise. And then I just print them. So I can run this cell to show you, and you could see them in this format. Okay, so we have for each strain value, we have a certain stress. After you construct your data, we can visualize them. And by the way, it's very important to live with your data. Like before you start running any analysis to try to fit a line or any other model, it's very important to try to understand your data and live with it. Like try to visualize it and to understand like the trends and patterns before we try to do machine learning. So in here, all what I do is just to visualize them, plot them on the X and the Y axis. So you can see the plot in here. So the strain is on the X-axis and the stress is on the Y-axis. And this is the data that I showed earlier. So you could see that like the figure is a bit big, the size. So I will show you how we can simply like right here, make it a smaller size to have like a smaller figure. But I want to show you something interesting how to do it. And this will be a motivation for something I will show later, how to use LLMs, large language models like ChatGPT and others to write and even execute code for you. So in here, we can go here. You see this button in here, this icon? This is for Gemini. So Gemini is the LLM by Google. So I can click here and I can ask it to change whatever I need in here in the code. Okay. Again, this is a motivation for the later section, but I need you to be careful because LLMs, they tend to hallucinate. Okay, so we need to be careful to understand whatever they're generating. We need to have the ability to understand and scrutinize what they're generating. So I can tell Gemini, for example, change figure size everywhere in this notebook to, for example, let's say 6, 6. And I click enter and it's working on it. And you could see how it changed it here and also later on as well. Okay. Once it changes that, you have the ability to say, I accept the edits that this LLM created for me. So I'll say for now accept, but make sure, again, I will review this all over again when we go to the other section regarding using coding, like LLMs to do coding and agentic coding as well. So I'll click accept and I can run the cell again. And you can see we have right now a smaller figure. So for now, I will just close in here. There's the close button for Gemini. After visualizing the data, we then introduce the concept, if you remember, of the residuals. Okay, so I constructed the figure actually here in Jupyter Notebook. So I will run the cell to show you where I define the residual, the difference between the line that we have, okay, the arbitrary line, and the data. Okay, so it's sigma I, in here we call it, minus sigma hat, correct? After we visualize the data, we need to decide on a loss function. And we discussed this earlier. We're going with MSE, so this is our loss function, and we can take its gradient or its derivative with respect to each parameter. In here, we're doing it ourselves. Like I said, in more complex machine learning models, the derivative or the gradient is done internally using these libraries that we use. And we'll talk about it when we do neural networks. In this cell, I'm just defining how I do the gradient descent implementation. So we define the step and also the gradient descent in here. In here, we're defining the learning rate, that's how many steps in total we need, and the initialization. So we start from 0 for W0, and W1, we start from 50 megapascal. I can run this cell now, and then we defined, in here, we're just defining the gradient descent, okay? Next, we can run the gradient descent. And you can play around with this to change the variable, the hyperparameters, and see how the sort of the convergence changes or how your final solution change. After defining the gradient descent, we can just run it now, and I click run, and you can see how fast it ran. It's just too fast to do 5,000 steps because the function that we're doing is just too easy. Recall that we also got our solution from the other method, which is the closed form solution. So I can also calculate it here and run the cell, and we get the solution. So you could see how similar they are, the closed form solution and the gradient descent. Afterward, we could just plot the best fit line from, in here I'm plotting the gradient descent one, but it's a similar solution like I said earlier if we're plotting the closed form solution. I also discussed the loss function, the loss curve. Plotting it is very important to monitor the loss function, how it's changing. So in here we can also plot it, and we're on the cell, and this is what we obtained, which is the same plot that I showed you earlier in the slides. In this section on symbolic regression, we will discover the deflection equation of a cantilever beam using genetic programming. Unlike linear regression, symbolic regression can find nonlinear closed form expressions. We will also dig deeper into training versus test dataset split and overfitting. In this section, we introduce symbolic regression, and we will do this through a problem of discovering physical laws. Similar to the previous section, first I will show you the slides, so where we can go over the concepts and make sure you understand all of this, and then afterward I will show you the implementation in Python. So let's get started. First, I will discuss the difference between traditional regression versus symbolic regression. 2, I will introduce the problem. This is where I show you the data, and data or the problem we're dealing with is a cantilever beam deflection. Next, I will introduce one of the most important methods in symbolic regression, which is genetic programming, and we will go over important concepts such as expression trees, crossover, and mutations. Next, we will talk about fitness and parsimony pressure. Next, we will discuss the discovered equation through genetic programming, and then we will compare it to the actual theory. Previously, I discussed generalization in linear regression, and here we will go into more details. We will actually split the data into training and testing to be able to see the generalization performance. In the previous section, I talked about linear regression. Linear regression is one type of traditional regression where the model form is fixed in advance. For example, for linear regression, we were trying to predict the stress sigma, and we said sigma is equal W1 times epsilon, the strain, plus W0. So we already assumed a certain form for the model. All what we had to do is we changed the parameters during training through gradient descent to be able to find these parameters that minimize the loss function. But the point is, in traditional regression, in here, like I said, it's linear regression, or it could be you're trying to fit a polynomial, like quadratic or even higher order. The point is, in traditional regression, you already assume a form, and these have like like you have a bunch of coefficients, and you're trying to change them through the gradient descent or other algorithms to be able to reduce the loss function. So the training only adjusts numerical parameters like W0, W1, etc. However, for symbolic regression, which we're discussing here, the algorithm searches over both the structure, operators, and variables, and I will show you what that means, and the constants at the same time. The results of symbolic regression is an interpretable closed form equation. And we will contrast that with neural networks. So neural networks, this is what we call a black box model, where it's like you can write them in terms of equations, but really super long equations, like with billions of parameters, and they're not that interpretable, and so they act like a black box. You have an input and they give you out an output, but the inside is sort of a little bit vague of what's going on. In symbolic regression, the nice thing about them is they will produce actual equations, okay? And you have not, like without assuming a strict previous form of the model that you're trying to fit. The most established symbolic regression method is called genetic programming, and this is inspired by biology, by the way, which you can read about, which evolves candidate expressions using operators inspired, like I said, by biological evolution. I always like to give an engineering example, and the running example in here is a cantilever beam deflection problem. We're trying to predict, you see here, the beam is on the right here, so we're trying to predict the deflection of a cantilever beam subjected to a point load here at the free end. So this is the deflection, and this is the length it has, okay? And then it's fixed at one side, that's a cantilever beam, and then it's free from the other side. So we're changing P, and we're changing L, okay? And we're measuring the deflection. For this simple problem, the exact solution is PL cubed over 3EI, and this is the Euler-Bernoulli equation. So this is a simple equation, and we already know it. And the idea is to verify at the end that the symbolic regression will be able to find or discover this equation. So we will pretend that this formula is unknown, and we're going to feed data, synthetic data, or it could be experimental data, to the genetic programming algorithm, and we're going to find out whether it will be able to recover this equation. For this problem, the data I'm going to provide, we're going to assume a steel. The section that we have for the beam is this one I'm showing here. So we have 50 millimeter in width and 100 millimeter in depth, and then we have a thickness of 4 millimeter. The moment of inertia, the one that we're going to plug in here, is 1.441 times 10 to power minus 6 m to power meter to power 4. And you can verify that for yourself. I'm assuming you're already familiar with the moment of inertia, so you can verify that for yourself, which is 1 over 12 b the outer h outer the outer dimension minus 1 over 12 b inner h inner to power 3. So you can verify that for yourself, where remember the beam is deflecting around the strong axis. So this is the strong axis, so the deflection or the bending would be in this direction. Okay, so you can verify that we obtain the same solution. So this is the problem setup. We know the equation, but we will not tell genetic programming or symbolic regression. We're not going to feed the equation there. So we're going to generate data, synthetic data, or like I said, it could also be experimental data. And from this data, you usually have noise, and we're trying to figure out if the algorithm, genetic programming, will be able to generate the equation. And you could see how important this is. Like you have a bunch of data and you can generate closed form solution from the data. The synthetic data that I generated is as follows. So we have 400 data points that I generated from the previous equation, and I added some noise. In here, I added 2% Gaussian noise. Okay, or you could use other type of noise when you're generating the data. And like I said, when I'm done with all of the slides, I will show you the script where you can change the variables, play around with it to make sure you understand it. So the inputs, remember we have two inputs, P and L, okay? And the synthetic data in here, I got a uniform sort of distribution of how I sampled them. So from 500 to 5,000, and the same thing with L, I also had uniform sampling from 0.5 to 2 meters range, okay? So this is the range we're dealing with. These are the inputs. We're varying the load and we're varying the length of the beam, and then we have an output, and the output is what? The deflection. So for different load and different length, we get different deflection. So we have these two variables, and then we can also put them in a table format, and I will show you that in the script. The point is here to just understand them. So we can have P in here, the first input, L is the second input, and gamma here is the output. So we're trying to predict gamma from the inputs, and we're trying to figure out if it recovers the equation that we showed in the previous slide. When we're training, I did not give the algorithm all of the data. Instead, to be able to test for generalization later, I split the data 70% for training. This is what the model sees during training, and 30% for testing. Okay, so the testing and the whole point of generalization during training, the model will not see the testing data set. Okay, this split means that we have 280 points for training and 120 points for testing. Something that is commonly used in machine learning is that when you have multiple inputs, like in here we have P and L, and they are on a different scale. Like you could see P is like 500 to 5,000, whereas the length of the beam is 0.5 to 2 meters. So they have different scales. Okay, there are many ways to proceed with this, but what we need to usually do is to make sure we scale them in a way that makes them, all of them, on the same order. So we call it order 1. Okay, we don't want them to be like 1,000 times each other, okay, the scale of each one of them. So you can reduce the scale of P, which is the big one, by whatever scale we have. Like it could be the largest value in the data set, for example, or other representative point, or other representative value. The same thing with the length, and the same thing with the output. So when we're proceeding with training, whether it's for symbolic regression or other machine learning problems, it's a really good idea to make sure all of your variables are on the same scale. And I want to emphasize that these are the important variables or the important inputs that we know, okay? If you have more variables, like thousands of inputs, then you need to make sure you're sort of extracting or emphasizing for the model the variables or the inputs that matter for the output, okay? But this is something we'll talk about in the last section. The symbolic regression algorithm receives only, so P, L, and gamma pairs, and it does not know the governing equation, okay? So we have synthetic data, or it could be experimental data, and we feed it to the algorithm. In genetic programming, which is the most important method in symbolic regression, we have the concept of expression trees. And this is how we represent equations. Like, think about it. The point is, we're trying to evolve equations, and at the end, we're trying to have the equation that we generate sort of at the end, the best performing equation, to resemble or to be as close as possible to the analytical solution in this case. So the way we represent equation in genetic programming is through something we call expression trees. In tree-based genetic programming, which is still the most common type of genetic programming, each candidate equation is an expression tree. It's made of internal nodes, like operators like plus, minus, etc., and leaf nodes. And these leaf nodes are terminals like variables, p, l, or constants. So what do I mean by that? On the right, I have an example. So let's say we have this equation. This is not like the final equation. This is just a random equation that I'm trying to show you. So let's say we have p plus 2 times sine p minus 1. Okay? So how can we represent this equation as a tree? And this is something that you will see a lot in symbolic regression, representing the equations, like I said, as trees. And the operations, these evolution sort of operations, they will happen on the tree level. So I will show you what I mean. This tree, we can represent it as what? Let's start with this part. So this is P, this is a leaf node, and this is 2, also a leaf node. So we can put it in here. You can see this is P, and this is 2, and the operation between them is just a plus. Okay, so we're adding them to each other. This part is what? This is sine, so this is an operator that takes P, and this is what you have here. And then minus, this is the minus 1. Okay? And both of these components are being multiplied, so we have the multiplication in the root. So this is the root, and at the end we have the leaf nodes, and we have the internal nodes that have the operators. This representation enables genetic operators to manipulate the structure of the expression, not just the coefficients. If the concept is not clear why we're doing this, that's fine. Like the whole point, like I'll try to summarize it. We're trying to evolve trees or expressions, or in here, like or equations, to better fit our data. Okay, we're not just changing parameters like in the linear regression where we just change W0 and W1. In here, we're trying to change the trees in a smart way, and I will show you how we do it, to be able to fit our data. A simple way to think about it is like, let's say you have a bunch of data, like a data that looks like this, okay? Okay, so it looks a little bit like quadratic, okay? And the point is, let's say you start asking yourself, like, does X fit this data? Of course not, like Y equal X. You already can tell, like, it's not, because this is sort of not linear. You can ask yourself, like, is it X square? It's like, yeah, that's better, but maybe because we have like a shift here, right? So we could say, maybe we can get better. So maybe it's X squared plus 1. But remember, X or X squared or X squared plus 1, they can be represented as trees, okay? So they can be represented as trees. So the point is, we will change the trees in a smart way to be able to evolve these equations and be able to get or rediscover the physical law in here. So how does this work? Genetic programming, like I said, is inspired by evolution, biological evolution, and we have an evolution loop. So I will state the steps of how it works. So you can start by a random population. What do I mean by a random population in here? You can start randomly generating equations first. They're not good, they don't fit your data, correct? So that's what you do first. You initialize random expression trees that most likely will have very high error. In the context of genetic programming, we don't usually call it error, we call it fitness, okay? So the survival of the fittest. With the loss function, it could be in here, or the fitness function in here, it could be mean square error. So technically it's just an error, okay, or a loss function. The point we're trying to do is we're trying to have to generate expressions eventually that minimize the loss function or maximize the fitness, okay? So after we generate the equations, random equations, we evaluate the fitness. So we compare them to the data, or in other words, we just calculate the mean square error or whatever loss we're interested in. And we ask ourselves, is the loss good enough? Most likely, from the first generation we generate these random equations, most likely they will have a lot of error because obviously they're random equations. So we proceed. We proceed by selection, and this is again inspired by natural selection. For example, we can have in the first generation where we generated, so this is generation 0, we could generate, let's say, 100 equations, okay? Equations. And remember, in equations in here, we represent all of them as trees. And then of course, a lot of them, most of them will have very high error because you just generated random equations and you're trying to see if they fit, like let's say the deflection problem we have. So they will have like inputs P and L, but they will be sort of in an arbitrary way. So most likely they will not fit your data. However, there's something smart about this here. If we pick or select, and this is inspired by natural selection, if we select the 10 best performing individuals, okay, the 10 equations or the 10 trees that have the lowest mean square error, okay, and you can take these trees and let them marry each other. And this marrying, sort of like, this is an informal term in here, we will do some sort of genetic operations on them, crossover, mutation, and it will happen on the tree level in genetic programming. And the point is, from these 10 trees, let's say you can generate the second generation, so this is generation 1, and you can generate 100 equations again from these best performing 10 equations from the previous generation, okay? And the point is, if we do this over and over again, so in here, in generation 1, we pick the equations that have the best performance, the 10 best performing equations, we take them, and from them, we do genetic operations on them and generate a new generation with 100 population, let's say here 100 individuals, and we keep doing this over and over and over again. And that's the whole point of evolution. That's how we exist. So it's the survival of the fittest. You pick or you select the equations that have the highest fitness or the lower loss or the lowest loss, and you keep doing this over and over again. So this is like, there's a lot of nuance in this, but this is a general idea of it. So we generate equations first randomly, then we select the best equations, and then we let them marry each other, and then we do this over and over again to generate the next generation. And we keep doing this until we have a termination criteria. So we keep doing this. So select, do the operations, the genetic operation, then evaluate the fitness again, and then we might have a stopping criteria. You could say it's like, I have, like, let's say limited resources, I only want to run it for 500 generations. See, this is one termination criteria. Or the other termination criteria, it could be when your loss function plateaus, like it doesn't decrease anymore, you could stop. So this is another termination criteria. Or you could say, if the loss function decreases to a certain value, this is where I want to stop. And I hope it makes sense a little bit by now. So the point is, like when I say 100 equations initially, this is a hyperparameter that you could pick. It's up to you to say how many initial equations you want to generate. And the 10 that you select, it's up to you. So these are all hyperparameters. There's a lot of default variables or values you could pick, but it's up to you, and it's very problem specific. So what are these genetic operations that I mentioned? Like when we pick the best performing equations, like let's say 10 or whatever, we can take 2 of them, okay? And then we perform genetic operations on them. Or it could be 1 and we do just mutation. And I will show you that in the next slide. But for now, let's say we have 2 equations and we know we want to do some sort of manipulation on them to be able to produce like possibly better offsprings, okay? Ones that could minimize the loss. Again, we do this a lot of times. Maybe you could generate offsprings or children that have a higher loss, which is not good. However, if we do this a lot of times over a lot of generations, we will have a tendency to have a lower loss. Let's say we start with parent A or equation A and parent B, and let's say this is the equation in here, you could see them, and then this is their corresponding trees. To generate the offsprings or the children, one possibility, again, this is random usually, we can take one branch in here and the branch from here, and we swap them with each other for the offsprings. So we'll have two offsprings. So offspring A, and this is offspring B, where we could see that this offspring A, took the branch, the blue branch, from parent B, and this parent A gave the green branch in here to offspring B. So you have new equations. And these new equations, you will see how they perform in your data. And we keep doing this over and over again. In crossover, simply we just select a subtree, okay, or a branch in each parent and swap them. Another kind of genetic operation is called mutation, where we introduce random variation to maintain diversity. So what do I mean by that? Remember when we swapped we swapped like the subtrees? The sort of the genetic makeup of the population, when we just swap them, sort of it's there, we're not changing it much. Like, yes, we're swapping trees to potentially lower the loss, but we don't have much diversity since they're sort of confined with that population. So mutation, when we do random mutation, we introduce more diversity to the population. There are many kinds of mutation, but one common way to do it is point mutation, where you replace a single node with another value. So for example, let's say we have, this is the original equation, okay? So it's just p times 2, and we can just randomly mutate this value by another value or another variable. Either it could be a constant or it could be a variable. So in here we mutate it, and instead of 2, we can just put L, and this is p times L. So this is introduces diversity to the population. There are other kinds of mutation, like subtree mutation and hoist mutation, where in here, for example, subtree mutation, replace a random subtree with a new one. And the whole point of mutation, like I said, is just to introduce diversity to the population that you have. If you understand like 60 to 70% of what I said so far, that's okay. These are just the general concept. You need to understand that in symbolic regression, we generate like random population, and then we evolve them through natural selection to be able to reduce the loss function, okay? And this is sort of the generation is done randomly, but the selection, we do it based on the loss function. The whole point is to reduce the loss function to potentially have an equation that rediscover the physical law. And this is not necessary, by the way, always like an equation, a nice equation with like the exact physical law that we have, like for example, the beam deflection. It could be an empirical like equation that you want to generate. So there's a lot of applications for genetic programming. In here, I want to introduce fitness and parsimony pressure. So fitness function is simply just the loss function. So it quantifies how well a candidate expression matches the training data. So like I said, this is just the loss function, and we can use mean square error, and this is what I'm going to use in the problem. However, I want you to remember something which we talked about previously about Occam's razor. The problem is when you're running genetic programming, you might end up with a problem called bloat. And the bloat happens is where the trees tend to grow in size without improving predictions. So they will try to grow big to be able to minimize the loss. Initially, they will minimize the loss because they're more complex. They have higher capacity to fit your data. But eventually, because it is the wrong equation, because they're so long and they're not sort of related to the actual physical model, eventually they will just bloat and they will not improve your prediction. One way to solve bloat is to introduce parsimony penalty. So your fitness function or the loss function is going to be mean square error, for example, plus another term. And this term is a constant c, you pick it, it's a hyperparameter, times the number of nodes. So what do I mean? What does this sort of imply? In here, it means if you want to reduce your fitness function, you can reduce MSE, but also you have to maintain a small number of nodes. So if you have like a low MSE, but a very high number of nodes, it will make your loss very high. And by the way, the number of nodes is just the number of, it's just simply the number of nodes in the tree. So for example, if I go here, this is like the number of nodes is 1, 2, 3. So this is a simple equation. But you could have equations like with 50 nodes, and this will have a higher penalty because they're increasing the number, the size of the tree. And remember, we're trying to penalize the size of the tree. So the bigger it is, the more it's penalized. This, like I said, aligns with Occam's razor from chapter 2. Among models with similar performance, you should prefer the one that have a simpler structure. So for the problem we're having, the deflection, which I'll show you later in the script, I just want to go over the sort of hyperparameters that we chose. So for the training, for the population size, I started with 450 equations and I maintained that number. So what do I mean by that? So 450 is the number of random equations that I generated. And again, initially they will have a very high error, okay? And I evolved them over 30 generations. So we keep doing this process that I said over 30 times, and this is when we stop. Again, it might, the algorithm might find the correct equation from the first generation, like the one after, like the 0th generation, or it could take more than 30. We don't know what's the best thing to choose. And this is again a hyperparameter that you, in order to figure out what's the best hyperparameter, we should split our data to validation data set, which I mentioned earlier. I set the tournament size to 5, and the tournament size is the number of equations from the current population that are randomly selected to compete with each other to become the parent for the next generation. So what do I mean by that? Let's say from the current generation, let's say generation K, let's say we have a bunch of equations like 1, 2, 3, 4, 5, and we randomly select them from the current population. And also we have another size, like another batch, 1, 2, 3, 4, 5. And these are different, and we can look at this tournament, and we pick the one with the lowest error. So let's say this one is the lowest error. And from this one, the other batch, let's say this is the one with the lowest error. So these will become parent A, and this will become parent B, where we perform the genetic operations that I showed you earlier. If you increase by the way, the tournament size to a very high number, it will sort of increase the pressure. Because remember, out of 100, let's say I put the tournament size to 100, it means I'm only picking, there's very high pressure, very high competition, like out of 100, you will pick one. So if we increase it too much, then you will increase the pressure. A default value is usually like 5 to 7. As for the function set, remember when we're swapping and we're changing and we're doing mutation, the branches, they have like certain operations inside of them. It was like multiplication, sine, and cosine. And this will be up to you to tell the algorithm what equations or what operators to try. In here, I just chose the plus, the minus, the multiplication, and the division. But you could add, if you know your problem, for example, has sine and cosine, maybe the underlying physical law, then you could say, it's like you can tell the algorithm, it's like try sine and cosine, exponential, or whatever you're interested in. As for the parsimony coefficient, the one that penalizes the size, the larger size of the trees, I set it to 2 times 10 to power minus 4, but again, this is a hyperparameter. And when we're doing the genetic operations, there's many kind of genetic operations that we could do. Like I discussed crossover and mutation, there's Hoist mutation, point of mutation. You need to set the probability of picking which operations to do. So for example, we want to say that we want 70% of the time when we're doing the genetic operation, let's pick crossover. Let's do a crossover. Okay, so these are also hyperparameters, but again, the important thing, the most important operation is usually crossover, because you're trying to exploit the population you already have to be able to generate good equations out of them. So you have the highest sort of probability of being picked is the crossover. Something that is useful when we're doing genetic programming is called linear scaling. So for each candidate, like equation that we have, fitness is evaluated after applying a linear regression model on the equation itself. So this will be your equation, and you don't directly compare it to the data, but you perform a linear regression model on that equation, and you compare it to the data. Why we're doing this? We're doing this because we want the genetic programming to focus on the structure and not the scale of what we're getting. This will be very useful. So we just focus on the structure of the equation, how it looks like, and not on the coefficient and the scale of the equation. I ran the genetic programming algorithm, and I will show you the script after we're done with the slides. And here again, we're just trying to understand. In genetic programming, we can watch the evolution. So for each generation, we have a bunch of equations, bunch of expressions, and some of them perform better than the other. So we could look at the equation from each generation that have the best performance. Okay? For generation 0, This is where we have random generation, so we expect to have a very high error, and also the equation that performs the best, it's going to be random, right? It's going to be like not that good. The size of that equation, the best performing equation from the 0th generation, has 43 nodes, and it looks something like this. So you could see it's super random, right? It doesn't perform well. And this equation does not have the form sort of we're trying to discover, which is expected. It doesn't resemble it. Remember, the form we're trying to discover is p, small p, l cubed, okay? Of course, the actual equation is p l cubed over 3ai, but in here, because of scaling and the linear regression that we do in each step, we have the form that we're trying to get. Just look at the form, okay? It's going to be PL. So P is just linear in here to power 1 and L to power 3. So we don't have that in this initial equation, which is expected. But remember, we had 450 equations in the 0th generation. So when we initialize the algorithm. So if we do tournament and all of this, and we do crossover and all of these genetic operations, the next generation, generation number 1, actually was able to find the form we're looking for. Now, can you imagine how fast this is? This is fast because the equation we're trying to discover is very simple. You're not going to always have that, by the way. But the point is, you could see how we started with the random equation, and when we do the genetic operation random, like crossover, mutation, all of that, and you pick the best performing one after these operations, it was able to be discovered directly after just one generation. Doesn't always happen. Most of the time you will run it for several generations, especially when your problem is sort of complex. And I kept running it for a total of 30 generations. So generation 2 to number 29, they kept the same equation. So this equation stayed unchanged because it stayed the best performing one from throughout all of the generations. So generation 2 to 29th, the best fitness does not improve because the correct form was already found. Okay, and remember, we did not feed the equation to the algorithm. It discovered it on its own, or discovered the form, and I will show you the final equation. And I hope this makes sense why this is very important in engineering. Like, you can start with data and you could generate an equation, a closed form equation for your for the problem you're dealing with. We can also watch the loss function converging, and you could see here, because we start with a high error, just the 0th generation, so in here the generation, and here is the fitness, where it's made of MSE and a certain parsimony penalty. So we can have here directly starting from a high value, and we directly drop to a very low value, and that's it, right? We stay constant. Remember when we did the scaling, so we can scale back after unscaling to physical unit. The symbolic regression discovered law is this form, okay? So this is the form that we discover. The discovered equation is made of two components. This component, which has the input variables that we're interested in, so PL cubed, which is the correct form, plus a certain constant, a very small constant. I'm saying small with respect to the values of the deflection that we have, by the way. If you compare it, remember the form that we know is PL cubed over 3EI. If you just look at this value, so 1 over, so the value that's multiplied by PL cubed, it's going to be 1 over 3 EI, correct? So this value, 1 over 3 EI, if you calculate it, this is the theoretical solution, you would get 1.1, etc., times 10 to power minus 6, which is almost exactly like the one that symbolic regression found. So the symbolic regression coefficient almost matches the theoretical solution, and the small additive constant, like I said in here, is very small. And by the way, genetic programming doesn't always produce clean equations, so feel free, like if you know there's a certain coefficient that got generated, you can just drop it out. It's so small, but make sure after you drop it out to compare the solution that you cleaned, the clean solution, to the data to make sure that you still have a very low error, an error that you accept. Everything we said so far was done on the training set. Yes, we discovered the actual physical equation, which is good. However, most of the time you don't have that, by the way. So you have your data, but you don't know the underlying equation, okay? So it could be experimental or it could be simulation data. So it's very important, like we said, to test for generalization. The way we do it is we split the data, and that's what we did here. So for the training performance, So this is the number of data points. So this is the metric in here we have. So 280 and 120 points in here. The mean square error was this value. And you could see for the testing, the one that was held out, we calculated the error on that, the mean square error. And you could see it's similar to the training value. And then root mean square error, so we just take the square root. And by the way, root mean square error has a value of meter here. So remember, mean square errors has meter square, so it's your deflection squared. Whereas the root mean square error is more representative of the physical sort of value you're trying to get. So we have also a small value here, and compared to also the testing data or testing value, they're also similar. So why is that important? It's important because when you're training loss or training error and the testing loss, they're similar. It means your model did not memorize the training data set. It was able to generalize to the testing. So that's good. Whenever you see the training and the testing loss similar to each other, we want them both to be low value. Okay. So when they're similar to each other, when you don't have much discrepancy, you know that your model is sort of generalizing well within the range that you have in here. Okay, so the range that we picked, the P and the L values. We can also report R square. R square is nice because it's unitless. R square, when you calculate it, which again could be done directly in the scripts, in the libraries that we have in Python. So this value, if it's close to 1, then you know your model is performing well. Since we have train and test loss or errors are nearly identical, we know that we have no overfitting in this case. And this is a good time to introduce something we call parity plots. When your output, in this case, is a deflection, is just a number, we can plot the measured deflection, like the measured deflection, so measured deflection, which is the correct value, okay, or the one from the data set, the ground truth. And you can also plot the symbolic regression or the machine learning predicted one. So we can plot them as x and y. So this would be on the x and this would be on the y axis. And these values, if everything is fine, they should be the same, right? So x should be equal to y if we have a perfect fit of the model. So if you see them cluttered around this this line y equal x, then you have good performance. So this is a perfect prediction, and you could see the points that you have, the blue points. This is the training set. You see them around this identity line. So we're doing well with the training, and similarly for the testing as well. So this is the same thing, but for the testing. So if they're aligned on the identity line, then we're doing well. What are the key takeaways of this section? And I will show you, by the way, this example. I thought it would be a good idea to show you how I use genetic programming in my research. So I'll show you after I'm done with just summarizing what we learned from this section. And then we will do also the scripts, of course. Like I'll show you the Python script of how we run symbolic regression. So the key takeaways: symbolic regression searches over equation structure, not just the coefficients like we did in linear regression. Genetic programming evolves expression trees. So the equations are sort of represented as trees, and we do selection, crossover, and mutation. Parsimony, remember, this is something we do to combat bloat and promote simple interpretable expressions. We do linear scaling so that we let genetic programming focus on structure by handling the scale and offset externally. So we don't need to let genetic programming evolve to learn these stuff. Symbolic regression is valuable, especially in engineering, where a lot of the times we have no close form relationship that is known to us. So the discovered expression is a heuristic. A heuristic means like it doesn't need to be exact. It's a good enough approximations for us. And always validate on a held out test data set to check for overfitting. Okay, and if you're trying to tune your hyperparameters, like the probability of crossover and or the number of population or whatever you're interested in, make sure you divide your data into three sections. So you have the train, where you train your data on, and you have validation. This is where you sort of like check by changing that, by tuning your hyperparameters and see how it changes the loss on the validation data set. So sort of some of the learning is leaking to the validation. Like it's true, you're not showing your model the validation data set. You're not training your model on the validation data set, but you're tuning that. You're sort of adjusting the hyperparameters to fit the data set, the validation data set. And that's why these sort of are important for training and validation of the like to tune the hyperparameters. But of course, you need to have a third set, which is the test set. So you only show the test set to the model only once, and not to train, but just to measure the error on the test to be able to see if we have generalization or not. Now we turn our attention to the implementation of genetic programming in Python. So similar to what we did before for linear regression, you can find the code under my repository in here, under my username, my GitHub username, and then it's under this repository, and then you can click chapter 3, symbolic regression. So we can open it here in a new tab. I will do a quick code overview to show like the big picture. And again, Python knowledge is optional for this course. And like I said, at the end, in the last section, I will show you how you can use LLMs like Gemini, ChatGPT to help you generate and understand the code and even run the code as well with agentic programming. So the point here is just to do an overview and understand the big picture. When you open the file, most likely you will have some codes already generated, like some output. So you can simply go to Edit and clear all outputs. First thing, we will import the libraries, and I don't need to write genetic programming from scratch. Like, what does it mean to do crossover? I don't need to program that. All what we need to do is to import libraries that already have that. So I'm using sort of the most famous library for genetic programming, so gplearn. So we can install it with pip, and then we can just import it as in here, like the genetic part of the module, we can just import it. So we can run this. In here, click run anyway. Again, only run code that you trust. So you could see it's installing and importing the library. In here, I wrote all of the information so that you see what's going on. This is the same thing from the slides. This is the physical model that we have of the cantilever beam deflection. All of the dimensions, I have everything here so that you can read it and understand it. Then we will do data generation. So this is how we generated the data. Like I said, it's uniform, and when we have uniform sampling, and then we added some Gaussian noise so to generate the data. So we can run the cell, and it generates the data in this formatting. So we have P is the load, and then L is the length, and this is in newtons, the load, and the length is in meters, and delta, the deflection, is in meters as well. We have 400 points of these that we split 70% into training and 30% into testing. Before we run the machine learning analysis, we could do some exploratory data analysis, and it's very important, like I said, to live with your data. So we can run this to see how your inputs, for example, the load in here and the length, we could see how they vary, like how the deflection would vary with these variables, these inputs. Okay, so you could see that, for example, for the load, you can deduce some linear, you could see some linear behavior in here, whereas for the length, remember, we know it's L to power 3, the relation between deflection and the length. But anyways, so this is the plot that shows that we have a nonlinear relationship. So you can live with your data, and we have the formula, but the assumption is most of the time you don't have the formula to begin with, and that's what we're trying to get. We split the data into training and testing, 70 to 30%. Afterward, we scale the data, and I said this is important, not just in here in genetic programming. This is important whenever you're trying to do analysis with a lot of variables. It's a good idea to keep them all on the same scale because it helps with convergence. So we can run this. Afterward, we do the linear scaling, and the point of linear scaling we mentioned in the slides is to make sure genetic programming only focuses on the structure of the formula we're trying to get, and not on the coefficients and the scale of it. So we can run this as well. This is also where I define the mean square error as well, so we can run this cell. You can see for all of the code cells I left a lot of comments, so you can go over them, and it's very important for you to do it yourself if you really want to go deep into this. But at the end, like I said, I will also teach you how to write code, run code, and even go with agentic programming in the last section. In here, I'm just writing a helper function that helps me write the equations in a readable symbolic Python notation. So I'll just run this. Sim9 is the sort of the most important thing that we're discussing. We don't need to write what is a crossover or what is a tournament, how we do it. We already just need to import the library that does genetic programming, which we installed and then imported. And then we specify what are the hyperparameters that we need. I wrote them here in Markdown so you could read them, but I just specify them. So you can play around with this and change it for your own problem, but this is how we specify it. So you could use this script for your own, whatever problem you're trying to study. So we can run this code, just defining them, and then we can run the genetic programming. So we can run it and it will start the iterations. So we run, and you could see how we're running generation by generation. And it's pretty quick, right? So it will run until generation 29th. So in total, we have 30 generations. And evolution is completed. We can look at the best equation from each generation. Okay, it doesn't mean I'm not saying the best one overall. I'm saying the one that is best per generation. So we can run this, and you could see all of the equations. For example, the generation number 1 generated this equation, which is the correct form. Later on, all of these, they are the best per generation, but they're not better than this one. So we could just keep this one on the side, sort of, because it's the best performing one. Later on, we don't have improvement because we already found the solution that we need. And here, I'm extracting the best performing equation from all of the generations, which is this one, obviously. When we have a complex problem, most likely the equation will also be complex. So it will not always be this clear that, oh, look, this is the equation. So just keep that in mind. Afterward, we can apply the linear scaling to go back to the actual unit to find the coefficients. And then we can run the evaluation metrics. So for example, here we can run this, and we can get the MSE and R-square, and you could see the values like we showed earlier. And then we have also the parity plots that we can plot for the deflection. So we can run the cell, and you could see them here, one for the training, and this is for the testing as well. We can also watch the convergence of the loss function. So you have the code to plot over iterations, the best loss overall over the generations, and it's a constant just after the first generation, because we directly found the solution, like we said, and it stays constant until we terminate the process. So I hope overall, like, the steps make sense. And again, you don't need to fully be able to write these. You're an engineer, so I'll show you a way to using ChatGPT and using other AI tools to understand and write codes like this. But you could use a script like this and change it to your own problem, and it's pretty easy. I thought it would be a good idea to show you how I use genetic programming in my research. So I have this paper in thin-walled structures where I did a prediction of maximum deflection of n-edge, thin-shelled, hyperbolic paraboloid umbrella using machine learning techniques. So machine learning, I use genetic programming and another variation of it. So this is how I used it. I had this complex structure that I was studying. So this complex structure is called the hyperbolic paraboloid. It doesn't matter what it is. The point is we had inputs, which is the rise of the hyper. And by the way, I don't have a closed form solution for this structure. So it's really complex to get. There are like bunch of coupled partial differential equations. So we cannot get the solution. The only way to do it is to get a numerical solution using finite element analysis. But anyways, that's outside the scope of this course. The point is, this is a very complex problem, and I was only able to obtain simulation data where we have inputs, like these inputs, the rise, the area, and the thickness. And I'm interested in, similar to the like the section I just showed you, and the corner deflection. So it's also the deflection of the structure, but I don't have, again, the closed form solution. But if I have the simulation data, okay, I can train genetic programming to produce closed form solution. And that's what we did. And it was a really good research, and it was the first time that's done on this structure. We have a complex structure that we don't know the closed form solution for it, and we were able to get it through symbolic regression. I hope this inspires you for whatever you're working on, that if you have something really complex and you don't have an equation for it, you can get either experimental data or simulation data, and you can run symbolic regression to get a closed form solution. After you get closed form solution, you could perform sensitivity analysis to see, for example, how does your thickness, the thickness of the structure, influence the deflection, for example, or whatever you're interested in your problem. Another thing we could also do is optimization. We could optimize, say like what is the certain rise in here, for example, in my problem, what's the rise that optimize the structure or reduce the deflection or whatever we're interested in to study after we get the equations. In this section on deep learning and neural networks, we'll classify images of concrete as cracked or not cracked. This chapter introduces deep learning, fully connected networks, convolutional neural networks, cross-entropy loss, accuracy, precision, recall, and regularization techniques like dropout and data augmentation. Welcome back. In this section, we turn our attention to neural networks. And if you want the big picture, let's say AI is the big field. So let's say this is AI. Neural networks falls under deep learning. So deep learning is a subfield of AI, and that's where neural networks fit. I'll try to do an overview and show you an example of how we use neural networks, and we will do it through classifying structure defects. So we will show, or we will teach neural network to detect if there is a crack in a photo or not. And if you want to see how neural network fit in the big picture of this course, previously we studied linear regression, where linear regression we had an assumption about the model. So we said sigma, for example, the stress, it was stress a function of the strain. We assumed it's W1 times epsilon plus W0, right? So we had an assumption about the model. For example, in here it's a linear model, and during training, all what we had to do is just to adjust the weights using gradient descent and able to fit the data that we have. This kind of model has a very low capacity, and we talked about this earlier when we were discussing overfitting. On the other hand, in symbolic regression, we did not make sort of much assumption about the form. So the form of the equation was just evolving through genetic programming. So evolve the equation or the expression. And this made us sort of search over a bigger space of the possible functions that could fit our data. Like unlike, for example, linear regression. So you have data and you're trying to fit the data through the model. In linear regression, you make an assumption about the structure or the form of the model. It was linear in linear regression, but it doesn't have to be linear like we said. It could be polynomial or like any higher order polynomial, not just necessarily a linear function. In symbolic regression, we did not make that assumption about the form. We let the equation evolve, so we had a bigger search space. The way I think about neural networks, and we will go over the details, it will be confusing the first time you see it. But the point is, neural networks, unlike, for example, linear regression or even polynomial regression, neural networks have very high capacity to fit functions. Neural networks are actually universal approximators, where they can approximate any continuous function you have. They don't have to be parabolic or higher order. They could be any functions that you have, and neural networks will happily be able to fit it. And remember, when they have a very high capacity to fit data, you need to be careful of noise, that they fit noise and overfit the training data. So that's something that we will talk about. But the big picture is, in neural networks, we assume a certain form through the architecture. We call it the architecture of the neural network, and we'll talk about that. But the capacity of this network is very high that they could fit sort of a very large and complex data. So I see the analogy of neural networks fits more with linear regression or other kind of regression and not symbolic regression. The reason is because neural networks we assume a certain form, but the architecture of the network, it has a very high capacity to fit data. It's totally fine if this is a little bit vague. We'll go over the details, and I hope it makes sense by the end of this section. Here's the outline. We'll start with the introduction to neural networks. Then we'll talk about the building blocks of what constitutes a neural network, which are neurons, activations, and layers. Next, I will discuss the difference between classification and regression. This is not specific to neural networks. This is more of a general topic in machine learning. Then we will discuss concrete crack detection dataset. So I will show you a dataset Some pictures have cracks, some pictures don't have cracks, and the idea is to train a neural network to be able to predict if we show it a photo after we train the network to be able to predict if the photo has a crack or not. Then we'll talk about training strategy, mini batch stochastic gradient descent. This is something that we discussed earlier, and cross entropy loss. So this is the kind of loss that we use specifically here for classification. Then I will discuss two kinds of neural network architectures, FNN and CNN. By the way, there are tons of types of neural network architectures, and each one of them fit sort of a certain task better than the other. Afterwards, we will discuss evaluation metrics, so accuracy, precision, and recall, which I think are very important from the engineering perspective. Finally, we will discuss results and regularization techniques in neural networks. So what are neural networks? Remember, in symbolic regression, we were inspired by evolution to arrive at the correct equation. In here, instead of doing evolution, neural networks are inspired of what we already have. Okay, so they're loosely inspired by biological neural system. Just like biological neural systems, neural networks are organized into layers that transform inputs into outputs through weighted sums and nonlinear activation functions. So every term here is very important in this sentence, and we will go over each part. And remember, if it gets confusing a little bit, remember all what we're trying to do is we have input, and we're trying from the input we feed it into the network, and we try to get an output. Previously, for example, I gave you the strain, and we're trying to predict the stress. And then in the symbolic regression, we had the length of the beam, and we have the applied load to the beam, and we were trying to predict the deflection delta. Neural networks have weights inside of them. During training, the model, the neural network, learns by adjusting the weights to minimize the loss function. And this is similar to what we discussed earlier. Like for example, for linear regression, we changed W0 and W1 using gradient descent to be able to minimize the mean square error. The concept is very similar even in neural networks. This is a super brief history of neural networks. If you need, or if you're interested in more reading, you could read that chapter in the guide. Things started around 1958 with the introduction of the perceptron. And a perceptron is a single unit inside of modern neural networks. And I will show you that in a bit. So it's able to find linear decision boundaries only. So what do I mean by that? So let's say you have like bunch of points like this is points of class, let's say class X, and you have other points that are class O. Okay, so a perceptron is a very simple model that can fit the data like this. So let's say you can separate them by a line, and this is sort of your decision boundary. You could say anything to the right or below in here of the line is like class O, and anything to the other side is class X. So this is a very simple model, right? Because imagine if your class is a little bit more vague and the points are more mixed up together, like the two classes are closer, and there's no, if you cannot find a single line that can separate them, then a perceptron will not be able to do the job for you. So this was sort of the early neural network history. In 1980s, there was the popularization of something called backpropagation, which revived multi-layer networks. And like I said, a perceptron is just a single unit, sort of that could easily learn like a linear boundary between classes. However, for more complex problems, like I said, it cannot do that. So we need to layer these units, and I hope it makes sense by the end of the section. So backpropagation revived multi-layer networks learning, and they do it in a very smart way, like how the training goes with multi-layer networks. And by the way, there wasn't always like this big interest. Like if you go back to the 70s and 80s in AI, there was a time where it was called AI winter, and there's multiple AI winters that happened where researchers and funding from the government, they lost interest in AI research because there were specific tasks, especially for language recognition, that they did not sort of solve it. And for neural networks, I would say the big jump happened in 2012, and this is when the deep learning era started, and there was a breakthrough in image classification with AlexNet. So this paper and this kind of network had a breakthrough in classifying images. And by the way, I have more information in the guide if you're interested to read more. This was the like a big jump. Like this paper introduced a big jump of how they were able to classify images into the correct classes. For example, right now we take it for granted. If I show an AI like a photo of an airplane, it will know it's an airplane. Like if you use Google Lens or whatever. This wasn't easy before 2012. Like the error from machine learning models, it was very high, and AlexNet crushed it. They performed very well, and I would say there was development on the definitely on the model, on the architecture of the network improvement, a lot of research on that, but also the hardware. So the NVIDIA GPUs and all of this, they improved, and it helped to push this deep learning era. Now I want to talk about an artificial neuron. So neurons, biological neurons, they're part of the nervous system. In here, the neuron, the artificial neuron, that's why we say artificial neural network. Artificial means it's not the biological one. This is one part of the neural network, but first I want to zoom in and understand what's going on inside this neuron. A single neuron with n input computes the following, okay? The first time you will see it, it might be confusing, but don't worry about it, you will get it over time. A neuron has two operations, two main operations. So we have the sum and the activation, okay? So I want to give an example. In here we have inputs from x1 to xn. The inputs could be, for example, the strain value, like this could be x1, for example. It could be temperature, or it could be anything that you're inputting, or it could be pixels, the values and the pixels of the image. As an example, let's say we have just three inputs, so x1, x2, x3. Okay, and these are inputs to the neurons. Like I said, it could be the global inputs, the one we start with, or it could be within hidden layers, and I will talk about it what I mean later. So let's say we have just three inputs. The first thing that the neuron does, this neuron, it takes the sum, weighted sum of these inputs. So Z, this is the weighted sum. So we have W1, that's the weight. See, that's the first weight. W1 x1 plus W2 x2 plus W3 x3 plus a bias term. So this is a bias term that we add, okay? And before I keep going with this, these weights, just like what we did with linear regression, and even the bias, this was like the analogy is the intercept, right? These are all learned during training. Okay, so we learn them during training. So after we take the linear, like this is just a sum, weighted sum of these inputs, and then we add a bias, this is just a linear transformation, right? We just do a linear transformation, so we cannot represent much things with it. It's just a linear transformation of like a weighted sum of these inputs. However, we can add a nonlinear activation, and this is where we introduce the nonlinearity part in the neural network. So the activation is we take what we did, okay, so whatever the output from the sum, this is Z, and we give it to a function we call activation function, and from the activation function we get something called activation, okay? So A, the activation, is a certain activation function, and I will show you what kind of activation function we use. But the point is, remember, this activation function has to be something nonlinear in terms of Z. Okay, because that's where we introduce the nonlinearity, and that's where we make the neural network more complex. That's the part that makes it very powerful. So to recap, we have the weights, and these are the learned connection strength. These are the weights, and again, we learned them during training. We have the bias term. This is the learned offset, and the analogy was the intercept, but again, in here, it's for a neuron, okay? And this is we also have the bias, which is the learned offset. The analogy was the intercept from linear regression. In here, it's just the offset at like that you could do that will change where your activation function will fire. And I'll hope it makes sense in the next slide. An activation is just the nonlinear function. And we have many nonlinear activation functions that we use in neural networks, and we're going to talk about it next. A sort of historically common activation function is the sigmoid function, which is this curve. Like it's something that follows this curve, okay? And remember, Z, so it takes Z as an input. So this is its equation, okay? So it takes Z as an input, and it's 1 over 1 plus e to power minus minus z. Okay, so the point is you map whatever z value you get, okay, and you map it to 0 to 1, okay, from 0 to 1. So it takes any value from 0 to 1. This function was popular but suffers from something we call vanishing gradient in deep networks. And vanishing gradient is something that I'll try to like briefly mention it, and you can read more about it in the guide. The point is, I'm trying to relate to something we already discussed. Remember when we're trying to calculate the function, the loss function we had in linear regression? We had j, which was our function, and it was a function of w0 and w1, right? And then to tweak the weights, to change the weights during training, we took the derivative of dj by dw0, and we also took dj by w1. Okay? When we were changing the weights, we used the derivatives to do that. So when we make a neural network, okay, part of the things that we will take the derivative of, it will be the activation function. And you will see if your neural network has a sigmoid in it, you will also take its derivative because it's part in the network. So you will notice that it has a small derivative. Like if I want to plot, it's roughly something like this, okay, the derivative of the sigmoid. So it has a very small value. And if you have it in multiple layers followed by each other in your network, the value will be very small when you propagate. So I will go back to the concept later of something called backpropagation. So when you backpropagate your gradient, you're multiplying by small values, and they eventually become very tiny numerically. So it vanishes over time. It becomes very close to 0, and your models will not update the weights well. This is the main motivation why there was a big sort of move towards something we called ReLU, or rectified linear unit. So ReLU is a very simple function. Okay, it's a nonlinear function. Okay, and it takes z. Okay, so this is sigma of z, and it's the max of 0 and z. So if your z is a negative number, if z is a negative number, remember what was z was? Z is the weighted sum plus a bias. So if your network, or sorry, if your neuron doesn't fire, then this ReLU will give it a value of 0. Okay, so if the weighted sum plus a bias falls into here, anywhere into here, okay, so this is the plot of the ReLU on the right. If it falls here, then we give it a value of 0. And if the weighted sum plus a bias is a positive number, then we just assign the number itself. It's going to be z. Okay, so this part, you see how it's a line here and a line here. So this is a nonlinear function, like both, if you add both components, this makes the ReLU a nonlinear function. The nice thing about the ReLU is it's very easy to compute, you could tell, and it's sort of the default choice in modern neural network architectures. But I want you to remember, this is the part that introduces the nonlinearity in neural networks. This is the main part that introduces nonlinearity. Now that we understand sort of the key component of a neural network, which is the neuron, the artificial neuron, now I want to introduce the architecture of the network. And I want to first introduce what we call fully connected feed-forward neural network. Okay, there is a lot to unpack here. But it will make sense by the end of this slide. So let's say we have a bunch of inputs. And I'll first discuss what we have on the left, and I will show you what, like, the architecture on the right, okay? And if you've seen this on the internet before, like this drawing for neural network, finally it will make sense here. So you could have input layer. So this is what we call layer. So this is the input layer. So I will highlight it here. So this is input layer, input. And these inputs, okay, we start from x1 to xn. This could be, again, it could be, for example, you're giving your network to predict the deflection. So let's say your x1 could be the p value, and x2 could be, for example, the length. And your output, the one you're trying to predict at the end, let's say like y hat, this could be, for example, what the deflection, okay, delta. So I'm just giving an example here just to make sure we anchor ourselves to things we already understand. So you have inputs, and this is the input layer. They could be like actual values or like something with engineering meaning, or it could be the pixels in an image, for example. And this is the one we're going to be using in here. Two, we have something called hidden layers. And hidden layers is where sort of the main learning happens, okay? And this is sort of when the hierarchy of features starts sort of packing on the top of each other. So what do I mean by that? So in hidden layers, we have weighted sum plus ReLU in each neuron, okay? And every neuron connects to all neurons in the previous layer. So what do I mean by that? I just introduced the neuron previously. So this part, you see these parts? Each one of them is a neuron, okay? And you could see what's going on, right? So we have many neurons, and this point, let's say X, this will has a certain value, and it will feed into this neuron, the one on the top, and into this one as well, and into this one as well, this, and this. And the same thing for all of the other inputs. So you could see how many weights we have. Like in here, I have W1, W2, W3, etc. Right? And also from the X2, when it connects to each one of them, this is other weights. Okay, so these are new weights. So the point is, each layer in here, like this is the second layer, hidden layer. This is a hidden layer. Hidden, we call it hidden because it's not the input or the output, it's the things in between, sandwich in between. So this is the hidden layer, and each neuron from this layer is connected to everything, to every single sort of part or component in the previous layer. So this neuron is connected to this input, this input, this input, this one, and finally this one as well. We already connected that. So I hope it makes sense. This is what we call fully connected. After we're done with this hidden layer, the first hidden layer, we feed the output of the neuron, okay, which was A, into another neuron. So first it was an output, now it becomes the input for the next layer. So this is another hidden layer, okay? So this layer, hidden, okay? And it takes the output, you see the activation is gonna come from here, from this neuron, and it feeds into this. And the same thing, and this neuron is connected to every other neuron, every neuron in the layer, the next layer. Okay, so you could see how many weights we have that we need to tweak in the network. So each one of them is connected. Each neuron is connected to all neurons in the previous layer. You could see that, and we can stack multiple hidden layers. And the more you stack hidden layers, the more nonlinearity you're introducing to the system, to the network, correct? And you could see that you can increase the size of your network in this direction, like you can increase the number per layer, the number of neurons in layer, or you can increase the depth. So this is what makes the connection that each neuron connects to all neurons in the previous layer. This is what makes the network fully connected. Okay, this is what we call fully connected layer. As for the feed-forward part, the reason we call it feed-forward is because the information flows from the input layer to the output layer, and it's strictly in that direction. So what do I mean by that? The best way to illustrate it is if I give an example where it's not a feed-forward, right? So let's say the output from this network, from this neuron, I take it has like whatever value, and I feed it back to this neuron, okay? So you could see how the information right now is flowing backward. It's a recurrent like connection. It's going backward. And by the way, introducing this recurrent connection changes the behavior of the network and what they can fit or how good they are in a specific task. Okay, and just changing that, you change the architecture. So this is what we call the architecture: how they're stacked, how they're organized, how the connection works. And I want to stress again, neural networks with this kind of nonlinearity, if you make it big enough, you can approximate any continuous function, and that's why they called universal approximator. And you can read about something called universal approximation theorem to understand how this works. Now it's time to discuss briefly the difference between regression and classification. So in regression, what we did in both linear regression and symbolic regression, the aim was to predict an output. So I gave you an input, let's say it was a strain, and from the strain, I want the model to give me the stress value, correct? Also, in symbolic regression, we did not make much assumption about the structure, like I said, of the function, but the input were P and L, and we're trying to predict delta. Okay, so these values are continuous values. The stress is like, it could be 5.3 megapascal, or the deflection, it could be 2 millimeter, 3 millimeter, or 2.1 millimeter. So these are continuous values, continuous output, and that's what we call regression when we're trying to predict something continuous. On the other hand, classification, which is what we're doing here with neural network, they assign an input to one of several discrete categories. So what do I mean by that? On the other hand, classification, which is what we're doing in this chapter, assign an input to one of several discrete categories. So what do I mean by that? Let's say we have a picture, an image of a car or whatever it is, like a certain object. I'm very bad at drawing. And then we're trying to ask the model, we're trying to train the model to predict if this photo contains a car or not. So the output that we're trying to get is either a 0 or a 1. Okay, giving 0.5 is meaningless, okay, in the classification. So we're trying to give like an output and assign it to a certain class. Now you could, for example, say I give a value of 0.6 to be a car, right? At which point we could say it's like, oh, you're more than 50% sure, then assign a value of 1, okay? And this is where like functions like sigmoid and others activations at the end in the output layer could make sense. But the point is, in classification, that the output that we're interested in is a like a discrete value. It could be 0 or 1. This classification, by the way, when we say is 0 or 1, 0 it doesn't have a car, 1 it has a car. This is what we call binary classification. So binary, just 2, 0 or 1. We could also have multi-class classification, for example, where we ask in the photo like what kind of vehicle we have. So it could be a car, it could be an airplane, it could be a motorcycle. You get the point. And in here, instead of just 0 and 1, we can have like a vector, let's say, a vector where the first row means if it has 1 in it, it means it's a car. So for example, this means that we have a car. If we have an airplane, we could say 0, 1, 0. If we have a motorcycle, it's 0, 0, 1, and so on. So we can hot encode it in a certain way. Okay. So the point is, we're dealing here with just binary classification. We want to give the neural network, we want to train a neural network by showing it photos of concrete, and some photos of these concrete, the surface has crack, and some photos it doesn't have a crack. And the point is to teach the network, or let the network learn whether, if we show it a new photo, whether there is a crack or not. First, I want to motivate the problem. Cracks in concrete structures such as bridges, buildings, and dams, they indicate degradation and potential safety hazards. Traditional inspection, like when you send a trained personnel to visually examine the surfaces, is time-consuming, subjective, and costly. Image-based machine learning, such as what we're doing in here for neural networks, offers a scalable alternative for rapid screening. Okay, so instead of sending a personnel to examine every single bridge and every single spot, we could use neural networks, and we could take the photos from a video or from a drone and whatever you have, and then we can run the neural network and let it examine whether we have cracks and where we have cracks, and then afterwards we can manually check if we see cracks. We can check how serious they are and assess them. As usual, I will show here the concept, and afterward we will do the code implementation in Google Colab. Okay, so the point is, as usual, is just to understand in these slides. The data set we're using is a very common. This is the source. You can check it out for yourself, and it's also found in the guide and also in the Google Colab. I have a link for it. So the data set we're dealing with has 40,000 images, and they're balanced. What do I mean by balanced? By balanced, I mean you have 20,000 photos that have cracks in them and 20,000 that don't have cracks in them. So this is what we call balanced, because you're positive, the one that has crack, and your negative, no crack, are balanced. The images we have are 227 by 227 pixels. Okay, so we can have like it's square pictures. Okay, and they made like these squares. We have 227 of them, 227 in this direction and 227 in the other direction. Okay, so we have 227 squares, 227 squares, and these are just like in 2D. But remember, images are colored, okay, and we usually express them as RGB, so red, green, and blue. Okay, so red, green, and blue, this is 3. So for each channel, this is what we call channel, so the red channel, the green channel, and the blue channel, they will have 227 by 227. Okay, so you can imagine it as what, if this is 227 by 227 is a matrix, then the 227 by 227 by 3, okay, so we have 3 of those because we have 3 channels, then this is a tensor. Okay, and I hope it makes sense. We're feeding the network tensors and not a matrix, because remember, each image, if it's a colored image, usually we express it as 3 channels. And by the way, in Google Colab, you can buy like more compute and like have a more powerful hardware to use. But I took a, like, just for the sake of running this easily, I took 20% of the dataset. Like, I didn't use all of the dataset. I only used 20% of it. So I trained the network on only 8,000 images, and I split them into 80% and 20% for training and validation split. I also resized them, so you can resize the images. Instead of using the full resolution, I use 96 by 96, which makes the training easier because we have less input. You can of course run it with the original size and all of this, and you can feel free to play around in Google Colab at the end. On the right we have images examples. So on the top we have examples of cracked images. So you can see this is the crack, this is a crack, these are cracks, this is a smaller crack. So these are all photos of cracks. And on the bottom we have intact surfaces, so we don't have any cracks in these images. Okay, so this is what we call the positive class. This is positive, that we detected crack, and this is the negative class where we don't have cracks. A good practice, a commonly good practice in machine learning, is to do data normalization for your inputs. I did something similar when we made sure all of our variables, remember P and L, the load and the length, in the symbolic regression, we scaled them such that they have order 1. We said we want them to have order 1. And the same thing with the output, delta. So it's a really good practice to have your inputs sort of on the same scale. It helps when we're doing gradient descent. It helps in convergence. In here, so the images were 8-bit images, so 2 to power 8 is 256. And this is sort of the range or the numbers of intensity units that we could have. So this could range from 0, or we could have an intensity of 255. So this is a total of 256 values. And this is the range of the pixels, okay, the values that they could take. With normalization, I could make all of the pixels range from 0 to 1. So I could take the raw value, the one that can take any value from 0 to 220 to 55, and divide by the maximum value, which is 255, and this maps the pixels to go from 0 to 1. So all of the pixels will have the same range, which they already have, but again, it's a very good practice to do data normalization in machine learning. This is especially important where your inputs, like when you have multiple inputs, they range with different values, like they have different ranges. When you do normalization, you make sure they're all in the same range. And like I said, it helps generally during convergence, gradient descent convergence. Another extremely important practice is data augmentation. So what is the data augmentation? It expands the training set with random transformation that preserve the label. So what do I mean by that? When I have an image, okay, so this is one image. Let's say I have just one image. I call this crack, right? Like this is positive, right? This is positive. We have a crack in it. But let's say I have a limited amount of cracks. And the whole point, remember, of training is to make sure we have generalization at the end. See, we want to teach the network a crack is a crack. It doesn't matter how I took the photo. Like I could took the photo like this way, or I could have rotated it a little bit or whatever. It doesn't matter. I could have zoomed a little bit. All of these variations, it would still make a crack a crack. It wouldn't change. And if you do that, you're sort of helping the network to understand the trend and not just to memorize in that picture of how a crack would look like. You're trying to let it understand the general trend. It doesn't matter whether crack or it could have different shapes, all of that. And we do that by doing data augmentation. Of course, we feed it a lot of data with different shapes of cracks and all of this, but we also do data augmentation. So let's say I rotate the image a little bit. This is the same image, and in the next picture in here, I'm rotating a little bit. So you could rotate it like 20 degrees minus or plus. And this image, it's still positive, right? So you increase your data by one more picture in here, which is helpful, right? And not just increasing by 1 point, you're actually helping the network not just fit that specific image, not to memorize that specific image, the first image, but rather to understand the trend, that there's a crack, so this is positive, and this is also positive. So it will tend to understand more the trend of what a crack means. The same thing if I flip the picture horizontally. So in here it's just flipped horizontally. The same picture here, but we flip it horizontally. We can also increase or decrease the brightness, and it would still be an image, a cracked image. And the same thing if we translate and zoom, or if we combine all of the transformation like rotate, horizontal flip, brightness, and all of this. So these kind of augmentation are very useful in neural networks. So these kinds of augmentation are very important when you're dealing with images. And I hope this inspires you for whatever you're working on. Like this kind of data augmentation, it's sort of like you can tailor it to the problem that you're having. Like you could have certain symmetries that you can exploit on your problem, and you could do it through data augmentation. As for the training batch size that we talked about earlier, when we deal with full batch, which we discussed, we sum over all of the data points we're trying to calculate the gradient, but this is expensive. I mentioned earlier that when we had just 10 data points in the steel data set, and I said like it's fine to take all of the data and take the derivative, like to account for all of the data per step. But when we have a lot of images or a lot of data, you don't want to do that. So instead we take batches of this data, and this is how we run the algorithm per step. So we use a subset, okay, of B samples, so the size of B instead of the N, the total data set size, and we use B samples per update. So how does this work? So let's say we have weights theta, you could call them theta or W, it's up to you. And then the update works. Let's say theta is like, I just want to make sure we understand this. So let's say this is theta 1, theta 2, etc. until theta L. And this is, let's say, if we have total of L weights in the network, okay? Or it could be W's, like I said. The way we update them is just the same thing like we did with linear regression, where we take the current value, okay? So the next step, we take the current value, and then minus a learning rate times the average over the batch size, and we sum over the batches, over each sample in the batch, and we just take the gradient of the loss function with respect to each of these with respect to each of these weights. Okay, so that's how we update it. It's very similar. Okay, and here we could have like W1, W2, or W1 and W0, and that's what we did in linear regression. In here we could have L number of weights, and L could be like, we could have few hundreds, few thousands, millions, or even billions of parameters in a neural network. You could see when we have a lot of parameters and the data is huge, this motivates obviously using mini batches instead of using all of the data set. So how do we pick the batches? We pick them through a stochastic method. So we randomly let the algorithm pick which points to pick when we're doing the gradient descent. This provides, since we're not using all of the data set, this provides cheaper update, and the stochasticity helps escape saddle points. Okay, I want to illustrate here something very important. Remember our loss function when it was a quadratic loss function before? It was something like this. Okay, and let's say this is the weight. Okay, let's say W0 for example, and this is your loss function of W0. Let's say we have just one weight. Okay, so this is the loss, or J. You can call it J. Let's just call it J to stick with the same notation. However, in neural networks, this is not like in here we just have a single minimum, right? Like this function, this loss function has a single minimum, and we have one weight. In neural networks, when you have hundreds or billions of parameters, we don't have a single global minimum. So it's not gonna look like this. So this function is what we call convex, where it has one minimum, and the minimum is the global minimum. Okay. On the other hand, when we're dealing with neural networks, and they don't have like a single parameter, they have billions of parameters, and these parameters affect each other, like these weights affect each other. Okay, so you're not going to have a convex function. You might end up with something, if we're just plotting the loss function with respect to one parameter. Okay, so this is g0. Okay, and it has obviously other parameters as well. It's not just a function of w0, but if we plot it with respect to w0, it's not going to be a simple function. It could look something like this. Okay, so the point is, with using stochastic gradient descent, because the parameters are coupled, you don't want to be stuck in a point that is like this, like let's say here or here. You're trying to approach the global minimum for that weight. Usually we don't arrive at that. We arrive at a good enough value, low value, by reducing the loss function. Anyways, I spoke this a little bit outside like the scope of this course. You can read more about it in the guide or online. There's a lot of material on this. But the point is, with stochastic gradient descent, you can escape some saddle points if you have a saddle point to go to the next minimum. Okay, the global minimum is not guaranteed in neural networks because the loss function decreases enough, and because we have the testing data set that tell us, or the validation data set to tell us if we perform well or not. So we get into a point that we sort of accept, but it's not necessarily the global point. I hope it makes sense. For optimization, we use something called Adam optimizer, which is extremely common right now in neural networks. So it's adaptive per parameter learning rate based on gradient momentums. Okay, it's faster and more stable, and it achieves a more stable convergence. And here, by the way, remember when we talked about learning rate, we fixed it. We said it's user chosen. In Adam optimizer, there's some hyperparameters that you can tune yourself as well. But this learning rate is adaptive. Okay, that's the adaptive part. So it changes, okay, the way it calculates, and the gradient, the way we calculate the gradient, to make sure it takes into account the previous gradients that you calculated. Okay, so you could read more about Adam. It's very common, it's heavily used, and this is what we use usually in neural networks. As for the epochs, every time I update the weights, this is what we call iteration. So when I iterate, I call it iteration. And the epoch is when I do one complete pass through the training dataset. Okay, so what do I mean by that? Let's say B, which is the sample I pick for mini batch, let's say it's equal to 5. Okay, and I'm giving a very simple example. Let's say I pick a batch size of 5, even though we usually pick a value of 32 to 256 for batch sizes. But let's say I have a batch size of 5. So each iteration, I'm taking 5 points or 5 images in here, and I'm doing the tuning, or I'm adjusting the weights of the network. And let's say in total, just for the sake of being super simple, we have total of 20 images. Okay. So each iteration, I do it when I take 5. So I take 5 images and I do the iteration. 5 images and I do the iteration. So that's what we call iteration. Okay. An epoch is when I pass over all of the training data. So the first batch would be 5. The second batch will be 5. The third batch also 5. And the fourth batch is 5. And I can keep going, right? But this is what we call, see, if we add all of these, the value will be 20, which means I passed over all of the training data that I have. See? Okay, so a full pass through your training data set is what we call an epoch. And this is what you're usually going to see in neural networks. When we train, we say we trained for 10 epochs, 100 epoch, or whatever it is. Okay, so the value usually is reported in epoch, and that's when you plot your curve. Okay, now of course we can also, like, when iterations it just happens inside the epoch, so you can have many iterations inside the epoch. So what is the loss function that we used? Previously for regression, we used MSE as the loss function, correct? And that made sense because we have a continuous value, a continuous output. However, let's say we have here binary classification. For this case, we often use binary cross entropy, or what we call the log loss. And something I want to mention here, when you see a log, like we engineers, when we see a log, we say it's log base 10. So when you say log 10 is equal to 1, right? This is what we usually say. In machine learning, I need you to change that a little bit. So usually when we say log in machine learning, we usually referring to the natural log, or what we call in engineering or math, we call len. So this is the natural log. Most of the time you see that in engineering, in machine learning, it's the natural log. So log of e is equal to 1 in here, okay? I hope that makes sense. So we use something called binary cross entropy or log loss. So how does it look like? Let's say you're summing the loss over n data points. Okay, so each data point will have a certain classification, and the output from the network will give you a value, and the value we need to assess how I should penalize it, right? If I do a wrong prediction, like let's say, I'll try to make it simple. Let's say the correct prediction is equal to 1. Okay, so let's say this certain prediction is equal to 1. So the image has a crack in it, right? It's a positive. My hope is my network, the predicted output hat, is equal to 1. Like I wish that, right? Like this is what I'm hoping for, that the network could predict that. If it does not during training, then we need to incur certain cost or incur certain loss. So we need to register that in the loss function, okay? And this is what the binary cross entropy does for wrong classification. So let's give an example. Let's say a certain image has a like a classification. Let's call it y1. It's the first image, has a classification of 1. So it's an image with a crack. Okay, it has a crack in it. If you plug this value in here, okay, I'm looking at here at this loss function. Okay, if we plug y1 in here, so this value is 1, and then this value becomes 0. You see, like 1 minus 1 is 0, so this whole term goes away, and you're left with, for this image, right, we're seeing the image, the loss of that specific image. Again, yes, we're summing over all of the images for now, okay, but we're now looking at just this value, okay. So y1 would be 1, and then multiply by the natural log of what I predicted out of the network. So what do I mean by that? Let's say I predict the value here to be 1. If the value is 1, the natural log of 1 is 0, correct? So this would be 0, and your loss would be 0, which is good. So you don't incur any loss. Perfect. However, let's say the image still has a crack in it, but somehow the network predicted a value of 0. Len of 0, or if the value is very close to 0, len of 0 is a very big negative number. So it's asymptotic to infinity. Remember, this is the plot of the len value, okay? So it's something like this. So if we have a prediction, the prediction, if it's a very small value close to 0, then it's a very large negative number. So we could have a very large negative number, okay? And for that image, remember, we're multiplying everything by minus outside, okay? So you have minus times a very big negative number, then your value, the loss, I would say like J1, okay, just for that image, would be a very, very large positive number, right? So we incur a very large loss if the classification is wrong. And you could test that if we have the other, like a negative image. If we have a negative image, this would be 0, and this would be 0, and this would be 1 here, and then you need to make sure that your prediction should predict a 0. Otherwise, you will incur, if you're close to 1, then you will incur a heavy loss. Our true label, again, just want to confirm we understand that the true label is either 0 or 1. Okay, you see, this is a set, not a continuous thing. This is just a set. So it's either 0 or 1. That's the true label. And the predicted label, the one with hat, it takes any value between 0 and 1. And we're trying, when we have positive class, a 1, we're trying to predict 1. And when it is 0, we're trying to predict 0. So this binary cross entropy, it penalizes the confident wrong predictions heavily, like we said. If we have yi equal to 1, but we predict yi to be close to 0, then the loss goes to infinity, okay? In PyTorch, and by the way, PyTorch is a library that is heavily used in machine learning, especially in neural networks. This is, like, remember when I said, like, we don't need to specify what a certain loss function is, like mean square error or whatever it is. This PyTorch, when you're building a neural network, you could build them in layers, and you could specify just the name of the layer. What do you want to call it? How many inputs it has? How many outputs it has? And it will build it itself inside. So you don't need to deal with that. And when it's doing the derivative of it, and that's what we call, like, when it takes back propagation, it derives the loss function with respect to all of the parameters and adjusts them. It does that itself. All what we need to do is just tell it to take the gradient. Okay, so it's pretty simple. So when we use PyTorch, you establish the network, you build the network in this library. Okay, so this library is heavily used, developed by Meta, Facebook. You can also have another library called TensorFlow. It's another one, but we mainly use, a lot of people use PyTorch. It's the most commonly used one to build neural networks. It's a good practice. So if you're interested to build things from scratch, like as a practice, you could do that. But whenever you're trying to do actual learning, you will end up using PyTorch or a similar library. In the Google Colab implementation, this is what I will be using. I will be using PyTorch. So we import it and we do everything with the modules from this library. We use BCE, okay, binary cross entropy with logits loss. And this kind of loss, it's not just a binary cross entropy, it also combines something we call logits, okay? So we have this loss combines the sigmoid. So it takes, so your network will give a certain value at the end, the logits value, what we call, and we take that value and we plug it into a sigmoid, the function, and this will cap it between 0 and 1, and then it plugs it into the BCE. This is better than having your network itself at the end having a sigmoid function. So this works for numerical stability. Anyways, it's commonly used in most documentation. We'll see it. It's very commonly used in binary classification. Now let's turn our attention to the first architecture that we're going to implement to classify the concrete surface dataset. So the first architecture is FNN architecture. We previously presented like how the input, the hidden layers, and the outputs are organized, and that was sort of the general architecture. In here, we have specific number of parameters that we used. So each image, and remember, each image was 96 by 96 by 3. 96 by 96 was sort of the square, right, of the size, and we had 3 channels. This is RGB. We flattened the image into a vector of around 28,000 values. And you might be already thinking, it's like, isn't it a bad idea that we're sort of discarding the spatial structure of the image? And you're right to think that, because in FNN, these feed-forward fully connected networks, when we flatten the image from an image from a grid-based image into a vector, a one-dimensional vector. So we have a vector, we turn it into a vector, and this is like around 28,000 values. We're completely discarding the spatial structures. And remember, when one pixel is close to the other, it means something, like a crack will propagate, or will have, like, it will sort of span multiple pixels, several pixels, or even the whole image. In other words, the spatial structure matters. So if 2 pixels they're next to each other, it would be a good idea sort of to exploit that structure. However, in such architecture, in such neural network architecture like the FNN, we discard that, which is a bad idea. I still wanted to introduce FNN because I wanted it to be sort of the baseline that we will compare to later on when we introduce the convolutional neural network, or the CNN. So how many parameters do we have here? In the linear regression, and I always try to anchor ourselves to make sense of what we're doing here, in linear regression we had W0 and W1, so we had only 2 weights, so that's why it was a very simple problem. In this FNN architecture, I considered almost 600,000 parameters or weights. So how does it look like? So the input layer, we have an input layer in here, and then it feeds, it has sort of 28,000 values, and then it feeds it to the first hidden layer. Okay, so the inputs become the input to the first hidden layer, and the hidden layer has 22 neurons in here, so the output dimension will be 22, and then this will be the output from the first hidden layer, and this will be the input to the second hidden layer. Okay, and then we give the output. Okay, and this will be our prediction. And in here you see I call them dense. dense and fully connected, they're used synonymously. So whenever you see dense and fully connected, they mean the same. So how does it look like? So let me show you in the dimensions. So we start 28,000, and then we go 22 neurons in the first hidden layer, and then we go 64, and then we go 1. So let me show you how it looks like. So if we go to the previous slide, so we would have, this is the first hidden layer, and this is the second hidden layer. In here, the number of the hidden layers, we would have 22, and in here, we would have 64, and in here just 1, and the input in here, we will have around 28,000 pixels, right? So you could see we have a huge amount of parameters that we can tweak, and we have a lot of nonlinearity. And I hope this is sort of starting to make sense. All of these weights, we will take like the derivative of the loss function. And remember, the loss function is quantifying how different we are from the ground truth value, the one that we have, because we already have like the labeled images, whether it's cracked or not. So we take the derivative of the loss function with respect to all of the parameters in the network. And this, by the way, derivative is already like we use the libraries like PyTorch that already has a very smart way to calculate the derivative via something called backpropagation. So we're going to calculate the weights, the derivative of the weights, and we're going to tweak the weights to be able to reduce the loss. And since like this network, like we said, it has the neurons, and the neurons have they have the like the sum and the activation function, and we have a lot of nonlinearity because of the activation function, which means we can approximate really complex sort of structure. And in here, we're trying to approximate or trying to conclude or trying to generalize what a crack would look like when we show it to a neural network. So the network is trying to understand that, okay? Even though we don't have an explicit equation of what a crack is, like what's the equation of a crack, this network, because it can learn very sort of complex structure, hopefully after we train it and we tweak the weights, it could conclude what a crack is in a picture. And again, I want to repeat, the idea that we took the image and we flattened it is a bad idea. It's generally a bad idea because we completely discarded the spatial structure. Okay, so that it does not. So the network I wrote here does not know which pixels are neighbors. Okay, especially the one that are, for example, this is a pixel here, and the pixel that is under it is sort of, it depends like how you unpack it, but the pixels are like the one that are in reality neighbors. We completely discard that and we ignore that, which is a bad idea. And that's why FNN are not used in image recognition, but I use it here, like I said, just for like as a baseline to compare it to the better suited architecture, which is CNN. So why CNNs? Why convolutional neural networks? In images, meaningful patterns like of the edges, textures, and in here cracks are defined by local spatial relationship. So two pixels that are close to each other, they could give us more information than just a single pixel. So when they're like taking in consideration sort of the pixel and its neighbor is a very good idea when we're trying to conclude something. CNN use small learnable filters, which we call kernels, that slide across the image. And this preserves spatial relationship and dramatically reduce parameters via sparse connectivity and weight sharing. So I will show you what that means. Additionally, they promote translational equivariant features. In other words, if there is a crack, and for example, in here, I'll show an image here, like if there's a crack here, or if the same crack taken like with a different photo and it's here instead, the same crack, then CNN easily deals with this, like and this is what we call translational equivariant. So if there is some translation of the crack or whatever we're trying to detect, it will still sort of deal better with it when it's trying to do like certain conclusion. In here it's classification. And before I show you the convolution or operation, let's say you have a certain like image and input or like just a certain matrix. We're gonna simplify it in here. Let's say we have 1 2 3 4 5 6 7 8 9. When we're flattening the image, we're writing it in a way as a vector, and the vector would be something like this. So it would be 1 2 3 4 5 6 7 8, 9. So it will be flattened in this way, and so we're discarding the fact that, for example, 1, 2, in here it's fine, 1 and 2, but we're discarding the fact that 1, 2, 4, and 5, for example, are next to each other. So this is discarded in FNN, but CNN, on the other hand, takes care of that. It exploits the fact that these pixels are next to each other, and it tries to draw a conclusion on the overall spatial structure. So how does it work? The equation of the convolution looks something like this, okay? So this would be the output of the convolution, okay? And this would be the kernel, like a certain component of the kernel. This is the learned filter, or the kernel. And this is the input feature, or it could be here also the input image as well. This equation might look a little bit complex, but it's not. So I will show you what's happening exactly. Remember the weights in the FNN? In here, they exist inside a filter, and there is way less of them because there is something called weight sharing. So what do I mean by that? So let's say this is a filter that we have here, and this filter is an example. I'm giving some like an actual numerical values inside this filter. This filter would have like the weights that's W1, W2, etc. So these are the weights that we're trying to learn, by the way. In here, I'm just giving an example of, let's say this is what we found eventually. And let's say this is your input image, okay? The output of the convolution operation of the kernel and the input image would be the feature map. So how do we compute the output or the feature map in here? The way we calculate, let's say, the output, if I want to calculate this value, it will be a matrix multiplication of the kernel and the first square here that has a 3 by 3 value, okay? So we sum over both the dimensions, okay? And this is what this equation is telling us, by the way. So if I'm interested in z 0, 0, you can perform the calculation, and you will find that it's a multiplication of this square and the kernel, okay? So multiply 1 times 1, 2 times 0, all of this, and then you just add them, okay? And this is the addition, and then afterward you add the bias. So for another example, if you want to calculate this output, I put it in green, and this is the one that I calculated here, highlighted. So this is in the value here is z1, 1. So the index, if we're starting, is 0. So the starting index is 0. So this would be z1, 1. The way we calculate it is by multiplying. So we're shifting 1 by 1. So this is the square that we're going to use, okay? And we multiply this matrix by this kernel. And you multiply element-wise, so element by element, you sum all of them, and then you add the bias. And here I didn't add a bias, and then you just get the value. So you could do this operation for all of the image, the convolution image of the input image, or the feature, and the filter. And remember, these filters, the weights inside of them are learned during training. We take the derivative. What happened here is that the output, like let's say this number 3, is not just sort of an output from one input pixel and another weight. Instead, it's sort of taking a contribution from the neighboring pixels, okay? So it's not just this value, let's say, multiplied by certain, like another weight, but rather it's all of these values multiplied by all of the kernel, and then they're summed and they're put in here. Just this small variation makes us exploit the spatial structure in the image and makes learning way better when we're trying to detect something in an image. In a CNN, we will have many filters. We have multiple filters, and each filter sort of will be used to detect different patterns. And this is not something you design by hand, okay? This is something that is all learned during training. Because I remember first time I learned it, it's like, oh, so we need to like sort of design the kernels ourselves, the values inside. It's like, no, they're weights. And the weights are adjusted with just taking the partial derivative and tweaking your weights, okay? But eventually, each filter will learn hopefully will learn something different from the image. And when the output, the final output, will take into consideration all of these filters and give us the classification, if it has a crack, if the photo has a crack or not. This convolutional operation is what makes a convolutional network called convolutional network. Another common operation that is used in CNN is called max pooling. The max pooling also has a kernel size, but there's no learned weights in it, okay? So if you want the equation, this is the equation of max pooling, okay? But it's better to always give an example. So let's say we have an input feature like this. So it could be the image or it could be the features inside the hidden layers. And we will have, let's say these are the values. So I color coded each one of them differently, each 4 squares. And we're jumping from here to here. So this is what we call a stride 1 when we're doing this max pool operation. If we were doing just a stride of 1, we would do this square first, and then we would jump just 1 square, okay? So stride 2, we jump 2 squares instead. So what does this max pooling do exactly? You simply look at a certain square, so let's say 2 by 2. So let's say the size of your max pooling is 2 by 2, the kernel. You could say, okay, we're looking here, and you just look at it and extract the maximal value. And again, this is all done by the code, okay? And the maximum value is 4.3. That's simple, okay? If you look here, the maximum value is 3.2. In here, the maximum value is 5.1. In here, the maximum value is 3.1. This operation reduces the spatial dimension by half. You could see how we started by 4 by 4 and we ended up with 2 by 2. This operation also provides local translation invariance. So what does it mean? Let's say in this red square, if the maximum was here, all the maximum was here, if it like varied translation a little bit, it wouldn't matter because the end result will still be 4.3 because we're taking the maximum in that region. And by the way, the max pooling is a nonlinear operation, and you could tell, right? So it's a nonlinear operation, and it also introduces nonlinearity in your network. So like I said, it retains the strongest activation, which is important because if you have some noise during the process, the network process, if you pick the highest activation, there's a higher possibility that it means something in the overall picture, in the overall picture of classifying the image, whether it has a crack in it or it doesn't have a crack in it. I want to note that not everyone in computer science or machine learning research is a big fan of max pooling. Some people have reservation, like it works, max pooling works, but some people argue it discards too much information. Instead, there is another technique that you could do to reduce the dimension. For example, you could do strided convolution. So remember, in the convolution, when we did here, the stride, like how much we jumped into the, like how when we're sliding the kernel, we're just jumping from here. Let's say we start from here, okay, to be able to calculate this value. The next jump was here, okay, so we were overlapping, and then to calculate the next value. So this is a stride of 1. We're just jumping 1. Instead, you could jump 2 squares instead. So instead of jumping 1, you could go here, and the next jump is in here. So this is a stride of 2, and this helps you to reduce the dimension. Another very common pooling operation is called global average pooling, or GAP. Similar to max pooling, there is also no learnable weights in this method. Global average pooling is often used towards the end of the CNN, and I will show you that in the next slide. What it does is, imagine you end up with a bunch of channels, and we usually, towards the end of the CNN, we end up with a lot of channels. They usually have small spatial dimension, each of these feature maps, but we have a lot of them. So what GAP does, it computes the mean over all spatial positions within each channel. So for example, let's say we have just 3 channels in here. We calculate the average of all of these values and we put it in here. And then also the blue one, of all the average of all of these values, we put it in here. The same thing here, and we put it in here. So what we end up with is a vector, one vector, the output vector from the gap operation that has it's one-dimensional vector that with number of component equal to the number of channels that we did the gap operation on. So we collapse each feature map into a single scalar. In the past, by the way, after we have a lot of the channels and the operations inside the CNN, we usually used to add a bunch of dense layers or fully connected layers at the end, which explodes the number of parameters or the number of weights that we have to tune. This gap method collapses this each channel into a single scalar, which means it drastically reduces the parameter count before we give this value or the output from the gap into the classifier. Unlike max pooling, which we discussed previously, the gap operator is simply a linear operation. So there is no nonlinearity introduced in here. It only helps in reducing sort of the number, the dimensions of the channels that we have into a single scalar, each one of them. Alternative to gap, global average pooling, we could do global max pooling, okay? And that would introduce nonlinearity. Anyway, so the whole idea of pooling operations is generally to reduce the number of spatial dimension, and this greatly reduces the amount of operations that we need to do and the amount of weights that we need to tune during training. As for the CNN architecture, it's different than the FNN architecture that we discussed earlier. The FNN, remember, each neuron was connected to all units or neurons in the previous layer. However, because the kernels, it's the same kernel that slides across the image or across the feature map, we have way less amount of parameters, and we have, this is what we call weight sharing, because there is a bunch of pixels that sort of share this kernel or the kernel weight inside. And by the way, when we're sliding the kernel, in here we usually represent it, just to make an analogy to image processing, we slide a 2D matrix. But in reality, remember, we have like a 3D, like the image is RGB, so it's represented in 3 channels. So the actual kernel is actually 3 by 3 by 3, so it's actually a tensor. But the idea stays the same. We have a lot of weight sharing, and the neuron is not connected to all previous neurons from the previous layer. There's many ways to represent a CNN when you're trying to draw it, but this should be a good representative way. So we start with the image, and the image was 96 by 96 by 3, and we start applying filters. For example, in the first convolutional layer, so we stack a bunch of convolutional layers, okay? And each convolutional block will have a convolutional layer plus the max pooling layer that we have. So we start in here, for example, with 48 filters or kernels, and each one of them is 3 by 3, followed by max pooling, and the max pooling, like I said, reduces the spatial dimension. Afterward, we have 96 channels or filters, and each one of them is 3 by 3, and then we keep going. So we do this several times. We go deeper and deeper until the last layer in here, the max pooling layer, number 4. And just before here, before we go into the global average pooling, the dimensions in here will be 224 times 6 times 6. So you can imagine it, we have like tiny 6 by 6 images. They're not really images, they're like feature maps, but they indicate something about the image that we input. And the global average pooling will collapse each of these 6 by 6 into one value. So we end up with a vector after the global average pooling that is simply 224 by 1. So it's just a 1D vector. And then we have what we call the logit operation, which is just a summation, a linear summation over the gap values over all of these the vector components. And during training, this logit value will be fed into the loss function, which was the binary cross entropy with logit. So it will take this logit value and it will penalize if we have the wrong prediction. And of course, during early in the training, we will have like the network will make wrong predictions, so it will penalize it, and then we take the derivative of the loss function with respect to all of the weights that we have inside these layers, and then we start tweaking them in a way that we would change the output such that we sort of be more compatible with the actual ground truth values. And you could see that because the architecture is different, the FNN versus the CNN, the sort of search space or what they're capable of searching over is different, and CNN is way more efficient because of because it exploits the spatial structure inside the image. So this weight sharing feature allows to have way less number of parameters, and we exploit the spatial structure. So neighboring pixels will tell us a bigger story than just one pixel. In total, if you sum all of the number of parameters inside the CNN, and I always do the analogy, when linear regression we had only two number of parameters, W0 and W1. In the FNN we had almost 600,000 parameters, which is a lot. In the CNN, I tried to make it comparable to the FNN so that when we're comparing the error later, like how they classify, if the classification is correct or not. So the CNN number of parameters we have is almost 500K. So we have less number of parameters so that the comparison at the end sort of seems reasonable. Before I show the results, I thought it would be a good idea to show how filter weights, the one that inside the kernels, how they, like these weights inside the filters, how they sort of help in detecting features, okay? And again, I want to iterate over and over again. These filters, the values inside of them, the weights, they're not sort of handcrafted. We just learn them during training. So we just get the loss function and we take the derivative and we tweak the weights in a way that reduces the loss function. But I want to give an example. We hope that for each task, by the way, there will be sort of more optimal weights or more optimal filters that we would learn for each specific task, okay? And I will go more into details, what's general and what's specific to certain tasks. So let's say we have this filter. This filter looks like something like this. So it's ones in here, zeros in here, and minus ones in here. So this is a 3x3 kernel designed to find vertical edges. So in here, let's say I handcrafted this just to show you how things work exactly. Let's say I have this feature map, okay? So this feature map, and I'm sliding this filter, okay, this W filter, and I'm sliding it over this image or this feature map. So you could see if I slide it, for example, this value, this 3x3 first, you could already do the calculation and you will find that, like for example, 1 times 10, 1 times 10, 1 times 10, 0 times 10, 0 times 10, 0 times 10, and then minus 1 times 10, minus 1 times 10, minus 1 times 10 times 10. So we end up with a value of 0 in here. So this is the result. Okay. So when we have sort of the same or uniform region, the positive and negative values cancel, and the same thing will be on the other side. And if you think of the values inside this feature map or this image, for example, as a like intensity of a certain color, let's say it's black and white or grayscale. In here, let's say it's full bright, like full brightness, so it's a value of 10. And in here, it's like dark, in here 0. So we have a vertical edge in here, right? Correct? So this is a vertical edge. And if you slide this filter, we will obtain this value, this output matrix, okay? So it will be zeros in here, and it will be zeros in here, and it will, in the middle, sort of when we have the vertical edge, it will fire. Why? Because the values on the positive, the values in here, if you slide it here, and the values on the negative, they will not cancel each other. So we end up firing in that region. And this is what happens. So we have values in here. So this filter will fire at the location to indicate that we have a vertical edge. I hope it makes sense. And this is how it works. Like this is handcrafted, but the filters inside the CNN, it will change sort of automatically to detect the features that are optimal to that specific task. Now I want to discuss the learned filters and feature hierarchy. I said I will iterate this over and over again so that we don't get confused about it. So learned versus handcrafted filters. For example, when you're doing when you're using a traditional software like image editing software, you use fixed hand designed kernels. So for example, if you wanna like add some blur to your image, or if you wanna sharpen the image, you could do that on the iPhone as well. So these filters are sort of handcrafted. Okay. However, when we're doing machine learning in here, like CNN, the filter weights are learned via backpropagation. And via backpropagation, I said, like it's the method with which we calculate the gradient or the derivative of the loss function with respect to all of these weights. So it's done automatically. So these weights are learned via backpropagation during training. So the network discovers the optimal filters for the task. So it's not like you're designing it yourself. And all what you have to do is sort of after you get your data is to sort of design the architecture, write the architecture that best suits your problem. If it's image recognition, most likely it's a good idea to use CNN, for example. And by the way, there are tons of neural network architecture, and each one of them fit one task better than the other. Another thing is I want to highlight is early in the architecture. I want to go back to this slide. We start with the image, and the image relatively has a higher resolution. And at the end, you could see here, like for example here, 96 by 96 by 3. And at the end, we end up with 224 images. They're not images, like feature maps. And each one of them is just 6 by 6. Okay, so I want you to think about it. The intuition is early on, we have very high resolution. And at the end, we have very low resolution, but a lot of information. We have a lot of channels, okay? Or a lot of images or something about that image. So we have 224 of that. What happens, early layers, the one that are close to your input, learn low-level features like edges, lines, and textures because the resolution is very high. However, as you go deeper to the right, okay, we learn increasingly abstract concepts like shapes, parts, and objects. You can think of it as squinting your eyes. So you cannot recognize the texture sort of anymore or the edges, but you will be able to tell like if this blob sort of looks like a cat or it looks like an airplane or a bike or a crack or whatever it is. So it will be more of an abstract form and not like high resolution image or feature map. And this is what we call that spatial resolution shrinks. Okay, so the spatial resolution shrinks, which start with 96 by 96, and we end up, for example, with 6 times by 6 before the gap operation. While the depth, the number of channels grows, and this is what sort of we highlight that the network trades pixel detail for semantic understanding. So we have a better understanding towards the end, like it's more of an abstract understanding. This feature, the hierarchical feature of learning inside neural networks, especially CNN, allows us to do something called transfer learning. Okay, so this is a very standard practice, and I hope it inspires you for whatever you're trying to, like the application you're trying to do in your own field. So we start with a CNN, like this is the steps of how it works, transfer learning. So we start with a CNN that is pre-trained. So we already trained it on a large data set, like ImageNet. ImageNet, by the way, is like bunch of, like it's sort of like a gallery for a gallery where it has millions, over 14 million images. So this one has over 15 million images, and it has over 20,000 categories, like airplanes, cats, dogs, all sort of things. And we have a lot of networks that people already trained. Okay, so you just take the file. That's with what I mean the file of the network. It's simply the weights of the network that sort of converge to fit to classify this network correctly. Okay, so we can take a pre-trained network and we freeze the early layers. By I mean freeze, we don't sort of change the weights in these layers, the early layers. Okay, so the layers that capture universal low-level features such as edges and textures, etc. Okay, so these are common, like universal features like textures and edges, and we retrain only the final layers to adapt to your specific domain. For example, in here, crack detection. And I hope the idea makes sense. In this course, however, we're training the CNN from scratch. Okay, so we're not using transfer learning, but it's something that you should know it exists, and it's a really good idea to do because it dramatically reduces the data and compute requirements. So you could only focus on the specific problem you have because all of the details, like the low-level details, already being captured in the pre-trained network. And this leverages billions of gradient updates because we already did all of the updates, especially like in the early layers that already performed on large scale data. And of course, this is valuable in our field in engineering where labeled data sets are often small. So we can already have the, like I said, like networks that already trained on low level, and we just need sort of squinting their last layers to understand, to like we tune them to understand the abstract things we're trying to detect. Now it's time to talk about performance or evaluation metrics. I want to highlight something very important that people get confused about, which is accuracy, the accuracy and the accuracy paradox. So if I tell you I have a model that has a very high accuracy, you should not always conclude that this is a good model. Okay, and this is why there is a paradox in here. So what is accuracy? Accuracy is the correct predictions over the total predictions. So what is the accuracy paradox? With class imbalance, remember our data set that we have for the concrete has 50% photos of crack and 50% of no crack. Okay, so that was balanced data set. However, let's say we have imbalanced data set where 95% of the photos that we took, which could make sense, right? Like most of the photos might not have cracks in them. Let's say we have a data set, 95% is negative. Okay, so we have no crack. If I build a model, like a very sort of naive model, and that always predicts no crack, no matter what kind of photo you show it, it predicts no crack for every image. This model will have an accuracy of 95%. It's a very high accuracy, right? So if we always predict no crack, will be 95% accurate. But it did not detect any crack for us, which means it's not useful at all. So it's very dangerous to assume that when we have high accuracy that we have a good model. You need to always look if your data is balanced or not, because if your data is not balanced, then high accuracy doesn't mean much. In our case, like I said, our data set is balanced, so accuracy remains a valid metric in here. But there are more important metrics that applies to here, the concrete data set, and engineering in general, that I think very useful for detecting errors or anomalies in the system. This brings us to confusion matrix, precision, and recall. So this is a new concept that I'm introducing. So I want to have a table. Okay, so your model will make some predictions, correct? A network, when it sees an image, it will say it's either crack, there's a crack in the image, or no crack, right? Sometimes it will be correct, and sometimes it's wrong, right? And the same thing, if it says no crack, it could be correct, it could be wrong, okay? So I want to make this into a table. Let's say the network predicts negative, and in here predicts positive, like predicts that there's a, like you can think in here, predict negative means predicts no crack, predicts positive predicts that there's a crack. However, we have the ground truth, okay, or what we call actual. So ground truth or actual. So we have actual positive and actual negative. If we predict negative and it's actually negative, then this is great, right? So if there's no crack and we say there's no crack, it's great. If there's actual crack and we predict that it's a crack, then we're doing well as well. Not all wrong predictions are equal. So what do I mean by that? From this matrix, the confusion matrix, I want to introduce two metrics. So precision and recall. So precision is true positive, okay? So true positive divided by true positive plus false positive, okay? So it's this value divided by this value plus this value. So what does this represent? In here, it's what the model tells you it's a crack, okay? But the true positive, the one in the numerator, it tells you if it was actually a crack. So in other words, this precision tells you if the AI flags a crack or the model that we built flags a crack, was it really or is it really a crack? Recall, on the other hand, is a true positive divided by true positive plus false negatives. So this is the true positive divided by these values, okay? So out of all of the cracks, out of the actual positives, how many did the AI find? How many did our model find? In structure inspection, for example, in here, recall is very important, right? So missing a crack, which is the false negative, so it's actually a crack, but we did not detect it, is more dangerous. Like there's a crack, but the model did not detect it, is more dangerous than a false alarm, okay? So a false alarm, we predict it's a crack, but there's no crack. So it would only require for us to go and verify that there's actually no crack, right? If it predicted there's a crack. But if there are cracks and we're not predicting them, that's a bad thing. So we have the data, two different architectures, we have the loss function, and then we can just run the training. And this is the training loss over 30 epochs, okay? So I trained the models, both of the models, FNN and CNN, over 30 epochs. So this is the FNN loss, and this is the CNN loss. And these are the curves, like how it's decreasing. And that's the whole idea, right? We're trying to reduce the loss function when we're training the network. I'm reporting two losses in here, like you see. So the training loss, that's the one that the model is being trained on, so it sees them. So train loss, and we have the validation loss. So this is the data set that the model is not trained on. So we only see if it makes good predictions on them, but we do not tweak the weights of the model, of the neural network, based on this data set, the one we keep on the side, the validation data set. If everything is fine, we're hoping that if we train it on the training data set, it will make good prediction on the validation data set. So we expect that the loss function to decrease on both data sets if everything is fine. For the FNN, we have both the training loss and the validation loss decreasing. It's a bit slow in decreasing. We stopped it at 30 epochs, but both of them sort of like show a healthy performance where both of them are decreasing. There's a gap though, okay? There's a gap in here, even though the validation loss is lower. So we expect less overfitting sort of, but we still have a gap between the validation and the training loss in here. So that's something to notice, and it's sort of slow while it's decreasing. On the other hand, for the CNN, we see a very quick jump in here, a drop in the early epochs, and then sort of it plateaus, and both the training and the validation loss are very close to each other. And also, we find that CNN in general achieves a lower error. You could see here the scale. So this is less than 0.1, and in here we have a larger scale. So the the CNN generally achieves lower error, especially on the validation dataset. In here we're comparing the models. We have the FNN and the CNN, so we have two hidden layers, and that's it. And here we had 4 convolutional blocks, and then at the end we have a gap, global average pooling. The test accuracy for the FNN is 87. And like I said, because we have a balanced data set, it's fine to use to report the accuracy. And for the CNN, it's 99.19. So you could see with comparable number of parameters, and even the CNN has way less parameters, right? So 500K versus 600K. CNN still performs way better than the FNN. The reason is, we mentioned it, CNN exploits the spatial structure like edges, textures, and crack patterns through the convolutional and weight sharing. FNN treats each pixel independently, which makes it unable to capture sort of directly these like this spatial structure. In here, I'm reporting the confusion matrix. So the green are the correct predictions, and the red are the wrong predictions. Okay, so the one on the diagonal in here are the correct predictions, and the off diagonal are the wrong predictions. And you could see, this is the FNN, you could see that we have way worse sort of performance. In here we have just 7, and here just 6. So generally, in here you could see that CNN performs way better than the FNN. Now it's the perfect time to talk about overfitting in deep learning. We discussed overfitting when we talked about linear regression, when we said it has a very low capacity to fit. And then we also discussed it in symbolic regression when we introduced the parsimony penalty, sort of to make sure we don't have the sort of overfitting problem in symbolic regression. So overfitting is when the model fits training noise and fails to generalize. A common indicator of overfitting, this is like when you see these two indicators, it could tell you that we likely have overfitting. So the training loss, when your training loss keeps decreasing, while the validation loss increases. So it only performs well on the data that you're actually training on. So it's sort of memorizing your data and not memorizing what a crack would look like. So it's only memorizing data and the noise in it. And also, when you see a persistent gap between the training and the validation accuracy, it's similarly, it's showing that it's learning more on the training data and not on the validation data. However, there is the idea that when we increase the model complexity, and I discussed this earlier, like when we do the segmental, like linear model we had in linear regression, we said it has a higher capacity to fit. This is true Also in deep learning, if you increase the number of parameters, you need to be worried about overfitting, however, to a certain degree. Because there is something I want to mention here, you should know it exists, and you could read more about it if you're interested. If you increase the model size too much, this does not always make generalization worse, okay? Because in deep learning, if we have highly over-parameterized regimes, it means when we have so much number of parameters, generally, the test error can decrease again, okay? It can be counterintuitive a little bit, but the idea is, there's a lot of research on this. The idea is if you increase the number of parameters in neural networks too much, then most likely you're sort of motivating smoother value or smoother functions to approximate, which makes the generalization go get better again. But again, you need to be careful that generally increasing the number of parameters is not always a good idea because it could lead to overfitting even in neural networks. So what are regularization techniques? We discussed one kind of regularization with the parsimony penalty when we said we're penalizing the more number of nodes we have, the more we penalize that. So we added a penalty to the mean square error, right? In here, I'm going to introduce a bunch of the regularization techniques, and these are the techniques that sort of reduce overfitting. So these are the methods we use to combat overfitting. We discussed one already, data augmentation. So when we do a random rotation, flips, brightness changes, this exposes the network to more variation so that it does not memorize like a specific rotation or a specific noise or something specific in that photo. So we tell it it's a crack no matter how we rotate it. It's a crack no matter how much is the brightness. It's a crack whether it's horizontally or vertically or whatever flipped. Another method to combat overfitting is called dropout. So how does it work? Let's say you have this network. Okay, so you randomly select a fraction of activations in these, like in the neurons, and you put them to 0 during training. Okay, so you can select like random numbers, and you could see them in here, and they are sort of dropped out. Let's say like 50% dropout or whatever it is, and you set that fraction to 0. Okay, so it's randomly selected, and it's done again automatically inside the libraries. This method prevents co-adaptation of units. So what do I mean by that? Let's say your network, sort of during training, it learned like the path from here to here and to here, let's say, and then to here. So if it started depending more on a specific path to classify an image. So it's just using a single path, okay? And it's not using the whole of the network to have a better solution, to generalize better. Okay, so if your network depends on a certain path, it's generally not a good idea. So what we do is we prevent it from doing this by dropping random number of activations. We put them to 0. However, during inference, what I mean inference is after you're done with training and you want to make a prediction. Okay, we do not we activate all of them. Okay, so the final contribution, it sort of will be an ensemble. Okay, this is what we call ensemble learning. So it will be an ensemble learning or an ensemble answer from all of the sort of sub-networks, okay, the networks that sometimes were activated and sometimes were not activated inside. So dropout greatly improves the generalization performance of a network. Also, we have early stopping. So early stopping is one method to prevent overfitting. So you can monitor the validation loss, okay, not the training, the validation loss, and you stop when you notice it has not improved for a specific number of epochs, okay? We call them patients. So let's say for 5 epochs I wait, if the validation loss hasn't improved, I can stop. Because if you keep running, then there's a possibility that your network will start memorizing the data, okay, if you keep it running for long enough. Finally, the last method I want to discuss here in regularization is weight decay. This is very similar to what we did in symbolic regression, where we penalize the sort of the number of nodes. In here, instead, we penalize the size of the weight, or like how big the magnitude of the weight. So if this is your loss function, J, the regular loss function would be J plus lambda, a hyperparameter, okay? And it indicates like how strong you want the penalty applied to the weight values, and then you sum over all of the weights we have. Let's say we have k a big K number of weights. So we sum over all of the weights we have, okay? So K1, K like W1, W2, W3 until all of the number of the weights, and we're penalizing the sum of these values, okay? And this is what we call L2 because this is squared in here. So we penalize the square magnitude and the sum of the square magnitude of these weights. And the hope is so that we discourage large weights. Like we don't want one weight in the network to explode or memorize the data that we have. And this allows for a simpler, a more generalizable model. So you will have sort of more more distribution, better distribution of your weights. So none of them like explodes and the other like go just zeros. These are the key takeaways before we go to the script implementation. So training is simply parameter estimation. So we're just tweaking, changing the weights to fit our data. So we define the architecture, minimize the loss on the data. That's the whole idea of it. CNN exploit spatial structure and dramatically outperform CNN on image tasks. And like I said, there's tons of neural network architectures. And for a specific task, let's say you want to do image classification, you could use CNN. If you want to do simple regression, and by the way, like we use them in here in classification, but I hope it's obvious that you can use neural networks to make regression, and I will show you how I used it in my research, by the way. I used it for regression. You can use FNN, CNN, or if you're coming from, for example, in structural engineering or fluid mechanics, you could use a specific architecture that was devised to better suit that specific task. The convolution operation learns local features, and pooling provides downsampling and invariance. Use cross entropy for classification and mean square error for regression. There are other types of losses, but in here these are usually the default. Use metrics that match decision cost. So for example, in safety critical application, you should prioritize the recall. So it's very important not to miss a crack if there's a crack. Apply regularization, augmentation, dropout, early stopping, and weight decay to prevent overfitting. Now it's time to do a code overview in Colab. And as usual, I will do a very brief overview right now. And the best way to learn it, and similar to what happened to me, like the first time I saw like a neural network learning, like a training code, it was a bit confusing. But the best way to learn it and grasp it well is if you actually do it yourself. So in the next section, I will teach you how to, like after this code implementation and all of this, I will teach you how to write the code, understand the code, run the code, and debug the code using LLMs such as ChatGPT, Gemini, and Claude. The idea is just to understand the flow in here, how it works, and then we will talk about like how you can implement it yourself next. And again, the best way is if you do it yourself and struggle with it, okay? So if you struggle with it, then you're learning. So we can open the code in here. So this is chapter 4, so we can open it here. There's a lot to discuss in this notebook, but I'll try to briefly sort of highlight the important things. And you can go over it. By the way, I wrote it in a way that you, like each section, as usual, like would have a lot of markdown in here. Like it will have a lot of markdown so that you understand what's going on under it, okay? So in here, I label it like step 1, what's going to go under it, and so on. And even inside, I tell you, like I write a lot of comments inside the code itself so that you see what's going on. And by the way, I did not generate all of the code myself. Like I reviewed it, made sure everything's working, but the code, the bulk of the code was generated by AI, by ChatGPT, Claude, and other tools. Two things I want to highlight is first, PyTorch. So we're going to import PyTorch, and I already mentioned PyTorch. So PyTorch is sort of the library where we perform, like we build our network and all of this. And the nice thing about this library is, first, it's open source, where you could implement, like this is where we implement mainly neural network or deep learning training. It mainly deals with tensors, and this is what we're dealing with here exactly. So it does tensor operation. It's optimized for tensor operations. Additionally, it performs automatic differentiation. Remember, I talked about backpropagation and all of this. So the derivative with respect, simply the derivative with respect of the loss with respect to the weights is done internally, and it's easily done in PyTorch. So you don't need to specify that yourself. And it performs, or it creates what we call dynamic computation graph. So when you specify the network, it knows exactly how the derivative or how the gradient will flow inside of it. So it can perform all of the operation, taking the gradient of the loss with respect to the weights internally. It also works greatly with Python, and this is what we're doing in here. So we're going to import PyTorch in addition to the other libraries that we use for plotting and like NumPy, the basic library for arrays. So we're going to import PyTorch. That's the one to build the network, like I said. And the module that we use to build network is torch.nn, or neural network. Okay, so we import it as nn. And this is the one that we use to construct the layers, the convolution layers, the linear layers, like the dense layers, all of these. And you can see there's a lot of tools that we use here from Torch to perform, like for example, data loading, splitting, when you're splitting the data, all sort of things. So it's already done for you. You just need to import them. And the more you see them, the more you will be familiar with how this works. Other thing I want to talk about in here, also a highlight, is CUDA. So when we're training the network, we're gonna train it on CUDA if CUDA is there. Okay. Otherwise, we train it on the CPU. So the CPU is the brain of your computer, right? However, the CPUs, and I discussed this in the assigned reading in the guide, so you can read more information in there. So the CPUs, each core inside of it is powerful, but it usually performs computations in series because there is not many cores. GPUs, on the other hand, they can perform way more computations, okay? So if you can parallelize what you're trying to do, the operation you're trying to do, it works greatly. So CUDA, developed by NVIDIA, the company NVIDIA, the one that develops the GPUs, okay? So CUDA, if you have an NVIDIA GPU, it will show that you have it, okay? So generally GPUs by NVIDIA. It's great to doing tasks like this. So the same GPU that you use for gaming, or the same GPU that people use to mine crypto, we use it also for neural network training, and it works great. The idea is, remember what I said, like we're training per batch, like we get a batch and we tune we change the parameters. So when you get a batch, you can parallelize the computation, right? Because we have a lot of images inside the batch. And this is great because CUDA, like the GPU, if it has CUDA in it, we can have thousands of CUDA cores inside of it, and we can just throw like the images per batch on it, okay? So this parallelization, doing things at the same time, like, you know, sort of multitasking, enables great like acceleration when we're training the neural network. So if you're running this on Google Colab, by default, usually we run on the CPU. But as a student, you can actually, like if you're in a university, you can get for free like a pro subscription in Google Colab. You don't need this, by the way, for here. But you can get a GPU to connect to a GPU. To enable the GPU, you can go in here, change runtime type, and you could change it instead of CPU like to other kind of GPUs. But like they will sort of take credits. You'll have certain amount of credits if you have subscription, and you can like choose the GPU that best suits your task. So anyways, most likely if you run this code, for in your case, you will have that you have a CPU instead of a GPU. The one I ran on this GPU, the RTX Pro 6000. This is also by NVIDIA, and it should work fine for this task. Next, I configured all of the hyperparameters that we need in here so that you could see what's going on. Remember, this is what I did for resizing the image. I said just to make the run faster. So instead of the full resolution, I used 96 by 96. This is the batch size that we discussed. This is per iteration. That's what we take. The epochs is the number of epochs we train with. And then the learning rate, this is the one that we use for the Atom optimizer. So you can see we have a lot of hyperparameters that you can tweak in here, and this is user specified. This is the validation data, the split. So we have 80% used for training and 20% used for validation. Again, all of this have a lot of comments so that you can go through them slowly and you understand what's going on. Early stopping, we said if the validation loss doesn't improve after, let's say, 8 epochs, then we could stop. It's like, terminate the training so that we don't consume more computation resources. As for here, this is what we call reproducibility. So each time you run your code, sometimes there is a random seed, what we call a random seed. So there's some stochasticity into it. Like each time you run the same code, it might generate different results depending on how you initialize your, for example, in here, the weights. Okay, so to ensure that you always get the same results over and over again, we fixed something called the seed, the random seed, and that's what I did. So it's a good practice if you're trying to present to people and you want to show them the same results over and over when you run the code. Next, the code here automatically downloads the dataset. So if you run the code, we will download the dataset from the link, okay, that we have here. I have all of the information here, and it will put them under data directory. You will have positive, the one with cracks. It will have 20,000 images, and then negative, okay? So that's what the code does in here. Afterward, I prepared the data augmentation. I also specify what we did with why we do data augmentation. And like I said, it's one of the regularization techniques, and it increases the sort of the diversity of your data set. So all of them with the comments, you could see them in here, what we did, like the different transformations that we did, the rotation, the shift, the zoom, etc. Afterward, we load our data set and we use PyTorch class called image folder to automatically load images from the positive and the negative directory structure that we got. So we only took here 20% of the like a random like number of random images, 20% from the original data set, like I said, just to run the code faster, to run the training faster. And we split whatever we got into 80 and 20%, 80% for training and 20% for validation. Afterward, we visualize our data. Like I said, it's a good idea to always live with your data before you run the training. It's a good idea to understand the structure of your data, how it, like what's going on exactly inside before we run any analysis. And it's always a good idea to ensure that we have good data. This is data visualization. So some of the images have, these are the one on the top, have no cracks in them, and the bottom I have with cracks. And like I said, we have balanced data set. We can also visualize our the augmentation. So the one when we did the flipping, the horizontal, all of this, all of the code, this is what it does, okay? So you can see that and have a lot of comments. So if we visualize that, you can see how it looks like. So this is no crack, and you can apply the different augmentation to it. So you could see all of this, and the one on the bottom with crack, and you could see also the different augmentation. Afterward, we define our neural network architecture. So first, we're starting with the FNN. FNN, by the way, it's also called multi-layer perceptron, okay, or dense network. This is another name. So it treats the image as a flat vector of pixel values. And we discussed this where it lacks sort of exploiting the spatial structure. So it has no knowledge of the spatial structure. So the input, this is just a markdown by the way I have here. So the image is 96 by 96 by 3. So we flatten it into a vector, and it will have almost 28,000. And we showed that in the slides. The first layer will have 22 units, and then with activations. Afterward, we have another dense layer with 64 units, and then we have just one output, which gives the logit output, and then later we feed it to predict the probability. This is very important here where we define the architecture of FNN. So when we build it, we inherit from the neural network module from PyTorch, okay? So a lot of the operations, the parameters, all of the structure, it will know that it's inherited from PyTorch, which obviously is great because we're not building it from scratch in here, okay? First, what we do is we initialize the different layers, and you could see like this is the flattening part, this is the hidden layer, the first one, the second one, and then finally the output one, okay? And when we when we want to tell PyTorch how we proceed with a forward pass, this is what we call forward pass, how the information flows, like how they're stacked together. Yes, you define them here, but you need to tell PyTorch how you're stacking them together, like how the forward pass is going to work, and it will internally sort of write the other graph, the other direction, okay, the backpropagation graph, where it could easily calculate the derivative of the loss function with respect to all of the parameters inside. So this is how it goes. First, we flatten the image. Let's say this is your input, okay, the image with the batch, okay. So your input will be a batch size, okay, and and the dimension or the size of each image. So this is the size of the image, right? Of each image. It's just a vector right now, and this will be the batch size that you have. Okay. So first we flatten, and then we apply the dense, like the dense layer first. Okay. That's the first layer, and then we apply activation to that, and then the other dense layer, and then activation to that, and then finally the output layer, which is just a linear layer of that. So it takes this 64 neurons at the end, and then takes them a linear combination or combination into just a single value. And this is simply the raw logit value that we will give to the BCE, the binary cross entropy with logits error. I included here to help you count the number of parameters. Counting the parameters could be done also automatically. I guess I have it here as well. But the way to calculate the parameters is like the parameter number for each layer will be the number of the neurons. This is for the fully connected, will be the number of neurons in the one that goes in times the number that goes out plus the number out, which represents the number of bias. Okay. So we can calculate the number of parameters for this network. Okay, they're going to be around 600,000. A lot of instructors don't go over like all of these details exactly, but I thought it would be a good idea, because if in your field you're trying to build like a network and you want to compare it to another architecture, like you want to compare FNN to another architecture, it's a good idea to have them like the same, like almost the same number of parameters, to have like apples to apples comparison. Afterward, we define some training utilities and the protocol. So the protocol goes as follows. So of course, like I said, we can define also the early stopping, like I said, so if the validation doesn't improve. And then under it, I have the training per epoch, and this is how we define it. So first you take the images, and then from the data loader that we defined earlier, and then you also get the labels of them, like positive or negative, and then you put them on device, and the device is the GPU, so we move them to the GPU. In the forward pass, the whole idea is to, first, we're not computing any gradient in the forward pass, so what we need to do is, but the output will be simply your model, whatever model you have, the network, this is your neural network, and it takes the images. Okay, so this is your output. It will give certain predictions like, yes, there is a crack, there's no crack, okay? And then your job is to compare the loss function. So your loss function will be a criterion, which we define, okay? And it takes the output from whatever your network predicted to the actual labels, the true labels. So this is the ground truth. So this is your predicted, and we compare them to the labels, and your criterion is defined here. So I define it below. So this is the BCE with logits. Okay, so you can see it here easily, directly. You see how we got it? We didn't need to implement it ourselves like the equation. We just define it from the neural network module in PyTorch. So this is what we do. When we run per iteration, we update our gradient, and then afterward, for validation, we know no gradient like updates. We just compare the output to the ground truth. And in here, we simply, after we define the loss function, I showed you here, the optimizer and the regularization, the decay, all of this, and we specify the schedule. By the way, learning rate schedules allows you to change the learning rate. So you could specify like after a certain number of iterations, I want you to adjust the learning rate. There's tons of like schedules that you could change, and it's up to you to choose whatever schedule you want, like how you reduce the learning rate. Like if you're already decreasing the loss function is decreasing, then you don't want to jump too big, like step size. So you could reduce that learning rate. In here, for example, we got a method, the scheduler, okay? And again, they're all inside the libraries, so you're not actually designing anything from scratch. We simply chose reduce on the learning rate when we have a plateau. We say when we don't have a reduction, reduce it by 0.5, and then wait for that to happen like five epochs, okay? And then we simply run the training algorithm for the FNN, and you could see the steps here. I already ran it previously. Afterward, we can have, like, you can save the model, and then you can just plot also, like save the history, and you can make a plot, and you could see the loss function decreasing in here. Okay, so I will zoom out a little bit. So you can plot this, and you can also plot the accuracy, and you can see it's increasing over the epochs. We follow the same procedure like in building the network in CNN. And again, everything is inside the libraries. You just need to sort of put your like layers how they're defined. So in the CNN, we took images and we do not flatten them, right? And then we had in the first convolutional block, we had 48 filters. Okay, each one of them is 3 by 3, followed by ReLU and then max pooling. Max pooling is to reduce the spatial dimension. Afterward, we do have another convolutional blocks and another one, and a total of 4. And then we end up with, like I mentioned in the slides, by 6 by 6. Okay, so 6 by 6, the size of the channel, and then we have 224 of them. So, okay, we have 224 channels, and then we take global average pooling, where you take the average of 6 by 6, so you end up with just a vector that has 224 components. So this is how we define it. As usual, we inherit from the NN, the neural network module, from PyTorch, and we define our convolutional layers. So in here we initialize them first, okay, and then this is the block, each block. So each block is each convolutional block is one convolutional layer, followed by pooling layer, okay, and so on. We can continue with all of them, and then in here we define the forward pass. And I said when you define that, PyTorch internally calculates the other way around to be able to calculate the gradient. So you follow with, you take your input, you get it into the convolutional layers, then you apply activation with ReLU, and then you take pooling, and so on. Okay, and at the end, when you're done, we take the gap and then we flatten that just to ensure it's flattened, and we simply apply the output layer, which is just a linear layer that takes the 224 from the gap, from the global average pooling, into a single value, and that value will be the logit value that we feed into the BCE with logit's error. As for the parameters count, we have way less, okay, number of parameters, like sort of per layer compared to the FNN, because not all neurons in this layer, in this specific layer, is connected to all neurons from the previous layer. So we have way more weight sharing in CNN, and that's why we have way less number of parameters. So we can calculate it manually, or we can also calculate it automatically as well using the model that we already constructed. So in the first layer, for example, we had 3 by 3 by 3. So this is the kernel size. And we had 48 channels, okay, or 48 filters. And then plus 48, okay, so we have the bias for each channel. This is plus B, right? And you can keep like going with each layer and doing this calculation manually. So this is the total count, almost 500,000. And in here, the model size for each FNN and CNN I reported here. As for the training, very similar to the FNN training, we follow similar procedure. And then when we run the training, you see how it's like each like accuracy and validation loss and all of this is being reported in here. If you scroll down, we'll see the training loss curve, and also here the accuracy on the side as well. As for the comparison, we can just simply, like we did in the slide, just put them side by side to see how they look like. So let me zoom out so that you see this. And this is the same slide, by the way, and this is what I got it into when I put it in the slide. So you could see the curves, both of them, like I said, is healthy. And I hope sort of that general idea makes sense of what went on. We have the data, we define our architecture, our loss function, we run the training, and then we just compare them. The more important thing is after we're done, we need to make sure, yes, we trained the model and they perform well on the training set. We need to make sure they perform also well on the testing data set, the one that we did not train on, right? So we could run here and report the confusion matrix, the accuracy, all of these things to make sure we perform well on the testing data set. So this is what this code does. So you can go through it, and then we can have here the results. We have the confusion matrix results, and this is the same confusion matrix I also presented earlier, showing that we have better performance of the CNN compared to the FNN. Similar to what I did in symbolic regression, I showed you a paper I published on symbolic regression to predict the deflection of a structure that was really complex. And here, I want to show you another paper that I have where we use neural network to make a prediction of wave pressure distribution on hyperbolic paraboloid surfaces. So in here, it doesn't matter the structure, right? It doesn't matter what's my input, what's my output. I want you to know that we have a lot of application of neural networks in engineering, okay, or in STEM in general. So what we did, we have inputs, we have outputs, and I did regression. So I did not do classification. And I mentioned already that neural networks, it's not just for classification. We could use them for regression as well. And even beyond regression, we can use them for sequence modeling or natural language processing. Like at the end of the day, ChatGPT and all of these LLMs tools that we use are simply neural networks deep inside. So what did I do exactly in this research? I was interested to predict a pressure. So this is my output, their actual values, and the output are 30 by 30 values. So it's like sort of similar to an image, not really here. It's just pressure values, okay? But they look like a grid, which could motivate using CNN, okay? So I had three outputs. So pressure at time t0, pressure at t peak, and delta t, which is a value, just a scalar value. Again, it doesn't matter what the outputs are. What matters is we're trying to understand the idea. So we have outputs, and I had a bunch of inputs. My inputs were something called normalized rise. It's a value, okay? It's like a continuous value. The draft of the breakwater, how much of the breakwater I have is immersed in water, and the wave height, okay? So this is a fluid mechanics problem, but also has a lot of down the pipeline, has a lot of application in structural engineering, and that's what motivated me to use this. Similar to what I showed you, I used FNN, CNN, and also another kind of network that I haven't discussed in this course, which is DeepONet. Whenever you're trying to, whenever you face a new problem, ask yourself or ask ChatGPT. You could discuss briefly the problem to these models and ask it's like, what kind of neural network architecture should I use? And it will help you to do that. And I will show you that later in the next section. So we used three different architectures, okay? And we were trying to compare how they perform. I also changed the size of the architecture, okay? So this tells you how much complexity they can represent. So I used two sizes, 50K parameters. Like I said, linear regression, W0, W1. In the CNN we were just discussing, we had almost 500K parameters. So I had two sizes, 500K and 50K and 500K. And this study, by the way, was novel because it's the first time where someone used neural network to study or to predict the pressure on the hyperbolic paraboloid surface. So this surface is pretty complex, and when we do analysis on it, it became more obvious to us that it's a good idea to use machine learning to perform prediction, okay? And of course, we use this, like the same structure, we used it because we lacked closed form solution. We used symbolic regression previously. So you can find this paper, by the way, if you are interested to read it. Again, you could be working in research, and I hope this inspires you. And you could also be working in industry, and there's a lot of application for neural network and machine learning in general in industry. And this is the structure we're dealing with. This is how it looks like. It's a breakwater. When the waves come from this direction, it attenuates, it reduces the wave so that we are safe on the other side, like there is no waves. And this is where this is the harbor where we put the ships or marina and stuff like that. When we're doing the analysis and publishing the paper, make sure you specify the hardware that you used and all of this. So all of the training settings and the code, I, by the way, linked at the end of the paper the script that I used for this paper. Next, we define the methodology, and it's very important when you're sharing research, whether you work in industry or you're writing a report, to share exactly the steps that you did. At the end of the paper, I also shared the code that I wrote to generate the analysis in here. So the way I collected the data is I used simulation data, okay? So similar like you could do in structural engineering, you could use finite element analysis. And here we use something called smooth particle hydrodynamics, where we simulate the water where we simulate water sort of as pseudo particles are interacting with each other. But the point is, we simulate the water and the waves interacting with the structure I have under different conditions. And these conditions are the input, okay? So it's the wave height, how big is the wave, how much of the breakwater is immersed underwater, so that's the draft, and also how warped, like what's like describing the shape of the breakwater. And we're trying to predict the water pressure, the wave pressure on the structure. So I hope this makes sense. Again, most of the time, writing the neural network code is easy. You can ask like LLMs to do it, ChatGPT and Claude. The challenging part will be to get good data. Okay, so getting good data and sufficient data is very important. And a lot of the times, getting data is very expensive, whether it's simulation or even experimental. And before I proceed, I want to stress that we did validate whatever you get from simulation data. Make sure you validate it against experimental data. I will skim over this because this is not related to machine learning. This is how we define the smooth particle hydrodynamics, the computational fluid dynamics paradigm. The same thing here of how I define the shape. And then in here, I define my loss function. So I define the loss function, its mean square error. It's some variation of it in here because I was trying to predict two outputs, like the pressure values, which is thousands on the scale of 1,000 of pascals, and a time, rise time, what we call rise time, like the sort of the time of the wave when it approaches the structure, and they are on different scales. Some of them is tens of thousands or thousands of pascals, and the other one is few seconds. So when you try to balance them, you could use specific, like specialized loss functions, and make sure also you could also normalize your data as well, which we already discussed. As for the neural network architectures, I briefly mentioned all of them in here. So you could see we have three architectures, the FNN, and you're already familiar with it. It's a multi-layer perceptron. It's a bunch of linear layers and activations. I use a different activation, like a Gaussian activation. Also, we have here the CNN and the deep operator network. If you want to know, if you're curious about the deep ONet, it's a network that tells tells the architecture that the calculation that you're trying to do, the mapping that you're trying to do, exists on a grid. Okay, so it's not just CNN sliding like the kernels, but in here you're enforcing the fact that you have the full output that you're trying to do exists on a certain grid, and this helps a lot in the flow of the data. Okay, and as expected, because my data I was actually calculating on a grid, it's not an image, it's actual pressure data, the deep ONet performed the best as expected. So this is how it goes, and we just proceed. I show some examples. This is the loss function that you're already familiar with. Then I do the metric, the mean square error. I do the parity plot, which I already showed before. Like when we're doing the prediction, if it exists on the perfect line, the identity line, then we're doing fine. And then also some predictions, like the ground truth versus the prediction from the different neural networks. Okay, so this is the surface or the wave pressure acting on the structure. As usual, we also need to do performance on the testing dataset that we held out, and we did other variations, like we tested if we change the model size to make it too tiny, how much does the error reduce, and which is the most robust architecture. And in here we found it's the deep ONet because it was sort of expected because we're doing the calculation on a grid. So I hope this inspires you for whatever problem you're working on directly, whether you're in academia doing research or you are working in industry. Let me summarize the main ideas from the course. If you remember only a few things, remember these. Loss functions define error. MSE is the standard default for regression because it is smooth and penalizes large errors strongly. Cross entropy, on the other hand, is the standard default for classification. Choosing the loss is one of the first modeling decisions. Gradient descent drives training. It updates parameters to reduce loss. Linear regression and neural networks that we covered rely on some version of this idea. Now, other optimization techniques to reduce the loss could be, for example, genetic algorithm, which we discussed during the section on symbolic regression. And by the way, there are tons of other optimization techniques to reduce the loss, but like we said, in most machine learning applications, we use gradient descent or some variation of it. In machine learning, generalization is the real objective. A model only matters if it works on unseen data. Memorizing the training set is not success. Validation is experimental design. Use training, validation, and test splits or cross-validation to detect overfitting. Split before pre-processing and think carefully about what information is available at prediction time. That is where leakage happens. Start simple and earn complexity. If a complex model cannot beat a baseline, it is not worth deploying. Symbolic regression searches for equations. It does not just fit coefficients, it searches over functional form. In engineering, that matters because integral equations provide insight as well as prediction. Parsimony matters. If two models perform similarly, prefer the simpler one. Small gains rarely justify major complexity. Neural networks are powerful nonlinear approximators. Their architecture encodes inductive bias. CNN, for example, work well for images because they exploit the spatial structure. Match the model to the data. Regularization is essential for high-capacity models. Data augmentation, dropout, early stopping, and weight decay help control overfitting. Performance metrics should reflect consequences. In engineering, errors are often asymmetric. Missing a critical defect can matter far more than raising a false alarm. Reproducibility is part of the result. Record seeds, save splits, and version data and code. If the result cannot be reproduced, it is incomplete. And finally, use AI coding assistants as interns, not oracles. They are fast and useful, but they still need supervision. Read the code, test the output, and understand the pipeline yourself. When you face a new machine learning problem, do not start with the fanciest model. Start by making the problem precise. Step 1. Define the question clearly. Specify the input, the output, and the context of use. How will the prediction support a real engineering decision? Step 2. Choose the metric before training. Pick a metric that reflects the cost of being wrong. Step 3. Build a baseline. Start with something simple and fast. If a more complex model cannot outperform it, stop there. Step 4. Guard against leakage early. Split before pre-processing. And only use the information that would truly exist at prediction time. Remember, the real goal is generalization, okay? So make sure you have data when you're trying to test for generalization. This data set should never be seen by the model during training, and it should only be seen once when you're testing for generalization. Step 5, iterate in the right order. Improve data quality, then features and representation, then model class, and only then hyperparameters. We focused on a core set of methods, but you will see many others in practice, and you can read and ask ChatGPT and search online about what is the best model for to use in your application. However, I thought it would be a good idea to show you few that are worth recognizing. Logistic regression, the standard baseline for binary classification on tabular data. It's fast, robust, and interpretable. Tree ensembles like random forest and gradient boosting, XGBoost, and light GBM, they are often the strongest default for tabular problems because they capture nonlinearities and feature interactions well. Support vector machines, they are strong in small to medium data settings. They're usually used for classifications, especially with well-separated classes. And in these models, you should pay good attention to choosing the right kernel, and scaling in these models usually become difficult. And there is also, by the way, support vector regression that we can use for regression tasks. K-nearest neighbor, or KNN, a simple non-parametric baseline based on similarity to nearby points. This is useful for sanity checks, but often slow at scale. So far, we talked about methods for fitting data, but you might end up with a lot of features and a lot of noise. So you might be interested in some applications to perform dimensionality reduction and use methods such as PCA. Some of these methods, dimensionality reduction, they help to compress your data, the features, do some denoising, and visualize high dimensional data sort of in a neat way. Clustering and anomaly detection. And by the way, I haven't covered clustering in here, but you should know it exists, and it depends of what kind of application you're trying to do. And a lot of the times you don't need to label your data. For example, there are news coming out every day, and each article, for example, could fit in a certain topic. Now, I don't need to label that. So for example, news article, but I can perform clustering operation, and most of the articles that, for example, fit certain category like science and technology, and the other ones about sports, you will see that they will cluster automatically close to each other, even if we haven't specified, for example, what's the name of each cluster, but after they're clustered, you can look and say, like, oh, that's sports, that's like science, that's whatever, right? So anyways, clustering and anomaly detection, this is useful when labels are limited or even absent. And structural health monitoring, for example, anomaly detection can flag unusual behavior, even without examples of every failure mode. And the nice thing about what we discussed in this course is most of the models are already like sort of programmed in mature libraries. For example, we discussed PyTorch. Your task is usually not to invent a new algorithm. It is to frame the problem well, choose an appropriate method, and validate it in the regime that matters. Let me close with an important part of modern workflow: using AI to help you code. You've probably already used ChatGPT or a similar tool to explain concept, debug code, or answer implementation questions. That is the basic workflow. Agentic tools go further. Instead of pasting errors manually, the system can run the code, inspect output, and iterate on fixes. Tools like Cursor and Claude Code can do this. These tools can speed up scaffolding, debugging, experiment setup, and visualization. But they can also create a serious risk: confidently wrong output. A result that sounds plausible, whether it's in writing or it's in code, may still be incorrect. So be cautious when using these tools. They're helpful, fast, and worth using, but not trustworthy without review. You also still need to verify outputs, validate results, and understand the full pipeline. That is why learning to code still matters nowadays. It is what allows you to audit the assistant. In the next video, I will show you this workflow in practice through screen sharing, using an LLM to write code, debug it, and then use Agentic tool on a larger task. Before we jump into the demos, let me give you a very brief idea of what a large language model actually is. An LLM, or large language model like ChatGPT, Claude, Gemini, or others, is a type of neural network trained on a massive amount of text. Its fundamental job is simple: given a sequence of words, predict the next word or token. That's it. It does this so well and at such scale and that it can generate coherent text, answer questions, write code, and have conversations. But how does it work at high level? The model is trained on billions of documents, such as books, websites, code repositories, academic papers, and others. Through this training, it learns patterns in language, like grammar, facts, reasoning, patterns, and coding syntax. When you give it a prompt, it generates a response one token at a time, and each token is conditioned on everything that came before it. A few things to keep in mind. Context window. Every LLM has a limit on how much text it can see at once. This is called the context window. It's measured in token. A token is roughly a word or a piece of a word. As a rough rule of thumb, one token is about 3/4 of a word or about 4 characters. So when someone says a model has 120,000 token context window, that's roughly 96,000 words, which is a decent sized book. Now we have models that over 1 million context window, and the trend seems to be growing. If your conversation gets too long and exceeds that context window, the model starts forgetting the earlier part. So for the long tasks, you sometimes need to be strategic about what you include in the prompt. Hallucination. LLMs sometimes generate things that sound completely correct, but are factually wrong. Sometimes they're not looking things up in a database. Most of the time, they're just predicting plausible sounding text. This means they can confidently tell you something that's nonsense. Always verify what their large language model gives you. Different models have different capabilities. Like GPT, Claude, Gemini, or other open source models, they all have different strength. Some are better at coding, some are better at reasoning, some are better at following instructions, and they're all improving, by the way, rapidly. What's state of the art today will be outdated in 6 months. Tool use. Modern LLMs can use tools. They can call functions like run code, search the web, read files. This is what makes them more than just a chat box. It's what enables the agentic behavior we will see later. Let me close with an important part of modern workflow: using AI to help you code. You've probably already used ChatGPT or a similar tool to explain concept, debug code, or answer implementation questions. That is the basic workflow. Agentic tools go further. Instead of pasting errors manually, the system can run the code, inspect output, and iterate on fixes. Tools like Cursor and Claude Code can do this. These tools can speed up scaffolding, debugging, experiment setup, and visualization. But they can also create a serious risk: confidently wrong output. A result that sounds plausible, whether it's in writing or it's in code, may still be incorrect. So be cautious when using these tools. They're helpful, fast, and worth using, but not trustworthy without review. You also still need to verify outputs, validate results, and understand the full pipeline. That is why learning to code still matters nowadays. It is what allows you to audit the assistant. In the next video, I will show you this workflow in practice through screen sharing, using an LLM to write code, debug it, and then use Agentic tool on a larger task. All right, so most likely you've already used ChatGPT, Claude, Gemini, or even open source models to ask questions. For example, you could say, I'm interested to do shawarma at home. Like, what's the recipe for that? And you will get the answer. Or you can ask things to stay up to date, like what's the news about like science and technology or other kind of news. In here, I want to show 3 use cases that you can use ChatGPT or other tools, other LLMs, regarding coding and more specifically in machine learning. The first use case is about writing code. Number 2 is to debug code. So if there is a problem with the code, you can ask these models to fix them. And then finally, agentic coding. Okay, and we will motivate the reason why we will be using agentic coding when I introduce the first 2 use cases first. All right, so let's start with the simplest use case, which is asking an LLM to write code for us. So I have the small CSV file, like with that with the stress strain data. Previously, we had them in just like directly imported because they're just 10 data points. But instead, I created them as CSV file, and you can find them in the resources. So I have them as like the strain column and then the stress column. So again, these data points are from the elastic region, and we performed linear regression on these data points. So let me upload this file to ChatGPT. And again, you can use Gemini or Claude or anything else to do this. For now, I'm using ChatGPT, so you can go to chatgpt.com or simply chat.com. To give it the file, you can click here, like add, and then you can add the file from here directly to access the CSV file. Or by the way, because again, there are just few points here, you can just paste the points here and it will get the points, it will understand them. But I will just drag and drop. So I will get the file and I will drop it into the ChatGPT box here, the chat box. Okay, and it's uploading, and it's just a small data set. Okay, so I'm gonna ask it this prompt, and I will give you this prompt as well. You can have it in the resources. So I'll paste it here. So I'm saying I have this CSV file. Let me zoom in. So I have this CSV file with stress strain data from the elastic region. The columns are strain and stress. And by the way, you don't need to specify these stuff, okay? This prompt is like too much detailed. You don't need to do that. I just wanted to keep it like sort of very elaborate first, but you need to understand that these LLMs, they have a better understanding of what you're giving them. So a lot of the things, they will get it from the context, from the data itself. So you don't need to worry about too much details. But it's good to specify in details if you want to make sure they fully understand what you want. So what I'm asking, please write a Python script that loads the CSV file. So we're saying it here like in step by step, which is a very good idea usually if you don't want the code to sort of go free on its own. For something simple like this, it's not a problem. But when you're writing more sophisticated code, maybe it's a good idea to give it step by step. And I even prefer the like to write code with the tab, which I will show you later when we're doing agentic coding. But anyway, so I want to load that data set and then perform simple linear regression, okay, from scikit-learn library, which it's a library where you can build a lot of machine learning models in. And then print the slope, which represents the modulus of elasticity. per percentage in here, okay, but we can make it as a fraction, and then the R square score. Afterward, we're asking to generate a scatter plot of the data with the best fit regression line overlaid. And this is exactly what we did before, and we did it in two ways, like I said, in the closed form way and also in the gradient descent way. And finally, we just label the axis properly with units and add the title. So again, this is actually too much details. You don't need to do that. If you tell it just to do linear regression, it will understand that. So I can send, click send or enter. And you can see how it displayed here, like how it displayed the data set. It's a small data set, so it's so easy to display. And right now it's writing the code. You see how it's very quick in doing this. Now, it wrote the code. This is something very important right now I want to say. So it wrote the code, right? And then you will see that not only it can run the code. So previously, like years ago now, these LLMs could just give you code. But right now they have tools that they can use. And one of the tools they can use is running the code, okay? So executing the code. So they have already like an environment, a Python environment, when you can execute the code directly in here in the chat box. So we could do this. You see here, you see the run icon here. So there's a run icon that you can click on it to execute the code. Or you could say it's like, just run the code, please. You could just ask it to do this, okay? So right now it should be running the code. All right, and now it finished. And you can click here, by the way, this is the code under this arrow, and you could find that it's the code that we requested. And it just performs the regression using the scikit-learn library, and it just does it through the linear regression model that it gets from that. So it's pretty simple. And by the way, this is deterministic. This is not linear regression. This is not gradient descent. So just doing linear regression directly using a deterministic way, which is similar to the closed form solution, sort of, okay? So the idea is we don't, it doesn't matter how we initialize, it's just always the same solution. We get the slope here, the value, and this is as per percentage, and we also get the R square value. And in here, you see the solution, like the linear regression line that it drew, and it adds a bunch of stuff, bunch of information to tell you what's the values that we obtained. And in here, it writes them also in a nice way to tell you what are the values that we obtained, which is similar to what we got before. So this is sort of the basic workflow. Like you describe what you want, you give it the data, and you let it write the code. For like straightforward models or something you were trying to do a task, this is very good. It's easy to do. This is a very simple machine learning model, linear regression. However, let's say you wrote a code or you got a code and the code has a problem. So the other use case I want to show you is how to debug a code using LLM. So I'm going to give ChatGPT a code, and this code, it's similar to what we're doing right now, but this code has an error, okay? So the error I will show you. So let me get the code, I will copy it, and this code has a problem in it. So I'll paste it here, and let me show you where's the error. So if I scroll, I will show you something in the data set that we got. You see that the data set has the first column called strain as a percentage, so that's its name, and the other one is called stress, okay? However, the code I gave it has an error. This is a very simple error, okay? Usually the error, it's going to be more sophisticated than this, but the point is just to show the application. So the bug I have, or the error I have in the code is here. So when I'm telling it to construct a data frame, so this is a data frame to get the values, I'm calling the column strain and not strain as a percentage or the actual name that it has. So if we run the code, this will give an error, and I'm asking it to fix it. So I can right now say, I'll remove the bug here, and you'll see how it will figure it out. And I'll say, fix the code below and let me know what's the issue. Okay, so I hope it makes sense. So you can simply ask it what's like the problem with the code, and it will fix it, and it will tell you. And it's a good idea to always ask what was the problem, because you don't want the LLM to hallucinate and fix something, or like fix something that you don't understand. It's always a good idea to know what was the problem. Additionally, if you're running Python somewhere else, like in VS Code or in any other IDE, and you got the error message, you can paste the error message and the code, and it will fix it for you. But again, this is a basic sort of implementation or use cases for LLM in writing code, and I will show you the agentic coding in a bit. So I will click send or enter. Now ChatGPT, sometimes they give you two options when like this is, they use it to improve the models. We're just gonna go with whichever one. So right now it told us what's the main issue. And this is what I like about LLMs, especially for simple use cases like here. So the main issue is that it uses the wrong column name for the string, okay, which we know. So we're saying the CSV columns are these, but the buggy code tries to access this, which does not exist. And then it gives the correct code, which you can also run if you want. So this paste, the code and the error is useful, but the applications of LLM extends way beyond this. Okay, so this is a very simple use case. If you want, like if you have a code and you want to understand it, you can ask, what does this code do? What does this line do? And you could do with the implementations I gave you, like the Python notebook, you can paste them here. And if you have any questions about the notebook that I had, you can ask it here. You can just paste the code and it will answer. Or we can go to something more sophisticated like agentic coding, which I'm going to talk about in a bit. So now I want to motivate using agentic coding. The problem is the workflow, copying the code back and forth, like with ChatGPT or other tools, it works, but it has some real limitations. And I wrote them down in my mind how I think about it. First, there's the back and forth. So every time like something breaks, you're gonna copy the error, paste it into the chat, wait for the response, copy the fix back, and run it again, which is a lot if you have a lot of code. For a simple like script, that's fine. However, for simple project with multiple files and dependencies, it becomes like a tedious task. Second, compute is limited. Like ChatGPT right now, the interpreter, when we ran the code, it runs on a basic server. Remember when I mentioned GPU versus CPU? And here just using a CPU. Maybe in the future they will make it more advanced and they will access maybe GPUs or something like that. But the point is, it does not have right now like a powerful GPU. So if you're training, for example, a neural network, or working with large data set, then it will hit the wall like very quickly. Third, and I think most importantly for me, the library environment is restricted. Like right now, we were able to access like scikit-learn, and there's also a bunch of good libraries in have here. But let's say you want to run symbolic regression, like we did earlier, and I want the GP-learn, like GP-learn library for the symbolic regression task. Like ChatGPT, the interpreter here, does not have, like in this environment, some of these libraries, like GP-learn doesn't have it, or more specific libraries like custom libraries that you can find on GitHub or somewhere else, they don't have them. So that makes it sort of not useful when you need like sort of more advanced tasks, especially related to engineering. So for anything beyond basic or quick scripts, we need better approach, and that's where agentic coding comes in. So in agentic coding, like this concept is when the AI does not just suggest code, it actually executes it. So it reads the output after it executes it, and it iterates on its own. So it feeds back itself the error that it got. So you don't need to do that manually anymore. So instead of you being the middleman copying the errors back and forth, the agent runs the code in your environment. Okay. So this doesn't run on the cloud on ChatGPT in a certain environment. You can run it. So the code will be running locally. Like the ChatGPT will be like, the LLM, the text it's generating is running on the cloud, but the code it's executing, it can run locally on your GPU. Or by the way, there is a way to host the agents, but that's way beyond the scope of this course. So the point is, you can have a more powerful GPU or hardware that you run on your own device. So the code runs the code in your environment, and make sure you always encapsulate it in a safe environment, by the way, when you're running code, especially with coding agents, just to be on the safe side. And so that if it installs something, it doesn't mess with your like a global library or the system that you have. So it runs the code in the environment, and then it sees what happens and then fixes things autonomously. As usual, I need you to be cautious. I mentioned this also earlier. You always need to be cautious because A lot of the time it generates code. It might mess up, it might hallucinate, it might pretend that it found the solution, and it does that so confidently. So you need to be very careful how you use these tools. It's always a good idea to read the code and ask it to explain it for you, okay? Because that way you will have a better understanding. So tools like Claude Code, Codex, VS Code, and GitHub Copilot, these like in the agent mode, they work like this. So these AI, they have access to your file system. They're also the terminal where they run the code, your installed libraries, and the GPU if you have one. So they can create files, they can run the script, read the errors, and keep going until the task is done. And again, be cautious while you're using them. So the whole idea is just to solve the problem, no more copy pasting like back and forth. So it handles the loop and it runs on your environment so you can get a good GPU, your own RAM, and your libraries that you installed if you have like previous libraries. And I repeat again, make sure you install it inside a virtual environment just in case to be safe on the safe side. So let me show you an example of how this works in practice. We're going to be using, there's a lot of AI agents tools that you could use like Cursor AI, Claude Code, and VS Code, Anti-Gravity, Google Anti-Gravity. There's a bunch of them. I'm going to go like with the most commonly used sort of software in that, which is VS Code. So you can install VS Code. So you can just Google install VS Code and make sure you install it for your correct system, like whether it's a Mac, Linux, or Windows. Most likely, if you're already using Linux, you most likely already know how to use this. Do you remember the symbolic regression data that we used earlier for the cantilever beam? So that data, you can have it as a CSV file. You'll have it in the resources. So I created a folder. You can place it anywhere on your desktop if you want to create and follow along. And this is the actual data that we have. So you can see the preview. So we have 3 columns. We have the force in newtons, the length of the beam in meters, and then in here, delta, the deflection. Okay, so this is something we worked on earlier. What I'm going to do is I'm going to open this folder inside VS Code. Okay, so I'm going to right click on this folder and I'm going to open it in VS Code, or you can find it directly here, like right click and also directly open with code, which is VS Code. Or you can open VS Code and open this folder in VS Code. So when we open the folder, I need you to notice that there is nothing here. So this tab is the file explorer here. We can see the files that are inside and the folders inside this folder. So the main one that we opened, okay? So this is when we're running code, it gets executed here. This is the file that I have here. I can click on it. You can view it here, by the way, on the right as well. You could see it. And the point is, I want the agent, and the agent, as I said, it uses LLM to execute code, but it gives back like the results and it feeds itself. So it has an error or any of that, it talks to itself until it figure out like the solution or the like the task to perform a task. So to open a new chat, you could see here, so Control Alt I, and it should be something different on the Mac, but the point we're trying to open GitHub Copilot, which has the agent mode in it. And I want to say the same thing. You could be using Claude Code, you could be using Cursor AI, you could be using any of or Google Anti-Gravity. There's tons of these tools, but the concept is the same. It's an LLM that when it executes the code using tool use, it talks back to itself to sort of achieve the task you're trying to do. So I'm going to open a new chat. I'm going to zoom in a little bit. So to zoom in VS Code, you can click Control plus. By the way, there are tons of things in VS Code, like you can connect it to GitHub, and if you're trying like to publish something, you can directly push whatever you're trying to do there. But the point is, we're just trying to make a very short demo of the agent mode. Right now, we have, if you come here, you see that there are multiple ways when you're running or interacting with this Copilot. So you can click here, and you could see there are multiple ways you can interact with it in terms of modes that they have. So this agent mode is the one we talked about. So it will keep going back and forth with itself. Now, if the problem is sort of complex and it requires a lot of steps to do, you can go into the plan mode, and it will does like a research and outline if you have multi-steps before it starts executing the code. So it's a good idea if you need if there's a lot of steps before sort of you try to achieve the main goal. If you wanted to if you just want to ask, it becomes more like ChatGPT, but it's like a regular ChatGPT, right? Or regular LLM. But the nice thing about it, in here, when you click ask, it's not going to run any code. It's just going to talk to you. And this is a great way if you have questions about your code or about your data. The nice thing, unlike when you go like to regular LLMs, which a lot of the times you will paste like certain data to them or the PDF or whatever, in here, it will have access to all of the workspace that you have here. So it has access to the files, which is awesome. Right now, I'm going to stay with the agent mode, okay? And by the way, for the model, remember, under the hood, it's simply a certain LLM that runs with the agent mode. So I'm going to keep it with the auto mode, and it should be fine. For more sophisticated things, it's a good idea to go and search the leaderboard for LLM. So you can just go on Google and say LLM leaderboard, and you will get a good answer on like what's the best model to use for your current task. Some models perform better or worse in coding tasks. So whatever I say right now, it might change in the next couple of months. So it's a good idea to stay up to date, okay? So I'm going to give it a prompt. This prompt, I'll paste it, and I'll show you the details. You can have your own prompt, but the point is we specify sort of what we're trying to accomplish, and that's it. It's that simple, okay? And you'll start getting a better grasp of this the more you do it. So I have the CSV file called cantilever_data with columns, etc. It will understand the data, by the way. I don't need to specify that. So please load the following. Load and explore the data. All of this, split the data. You can leave it up to it to do the split, and it will do the default. Normalize or standardize the data. And in here, this is the data that we use for symbolic regression. And I wanted, instead of using GPLearn to do symbolic regression, I thought it would be a good idea to show you how neural networks are also capable of regression, which I mentioned. We use neural networks for classification, but we can use them as well for regression. Okay, they're very powerful in that as well, especially when we're not looking for a closed form expression, right? Like symbolic regression. So in here, I specified that use a neural network. Just it will go with the simple one, feedforward neural network. Use the loss and which optimizer. It's pretty simple, and which metric, and generate the curves, the one that's going to decrease, and then bunch of other requirements that I have. Okay, so it's a very like sort of detailed task, and I'm just gonna click run. I'm gonna send it, and I'm gonna put it in the auto mode and in the agent mode. Okay, so now it's working, and it's gonna start checking the workspace, and it will show like the steps that it's doing while it's working. So right now it's saying planning. And the nice thing is most of the time it will work, this thing. So it will generate the code, and it will run it, and it will generate all of the like sort of the plots and show you the metrics that it will generate. So the nice thing about it is when it's going to generate the code, it's going to create them here. You'll start seeing them being created here. You already see that here. And then it's going to run them. And then if it has an error or anything, it will talk to itself. Now, most of the time this works, but I noticed from experience, a lot of the times it gets bored, and at the end it tells you, oh, these are the results, and it might not be what you're interested in. So it's always a good idea to check what's going on. So it created a Jupyter notebook, and it's asking me to run it, like open it and run it, but I don't want to run it myself, right? Because right now when it does a Jupyter notebook, it didn't run it itself. So instead, I want a regular Python code, and it's more comfortable running the Python code. So I'm going to say here, please use .py instead, and delete the Jupyter notebook, file. Enter. So we're still right now in the agent mode, so we expect it to run the code itself. And whenever it does something, it will tell you how many lines it created and how many lines it deleted in here. Now, since it's the first time, it's deleting. So this is the code that it sees it runs. It's asking me for permission. Always proceed with caution. And I'm going to ask it to allow right now. So allow for now to delete the file. And now you see here on the side how it deleted it. And it created these new lines, all of them new lines under this file, the cantilever analysis file. It created it in here. So I'm gonna click keep. So we can skim over the code to see. Again, always a good idea to proceed with caution and make sure you understand what's going on. So in here, instead of using symbolic regression, we created a neural network to do that. And you could see here the layers being created, like linear to ReLU, another linear with ReLU, etc. Right? And then we just run the iterations, the gradient descent. We're using Adam, and we proceed with 500 epochs as the maximum number of epochs. Usually it runs the code. Most of the time it will work, but again, sometimes it misses that. So it's like for right now, I'm gonna say like run the code yourself, please. It's asking right now permission to run the code. So I will ask it yes. Okay. Sometimes you can just let it by default run. Again, proceed with caution. Okay. So it ran the code, and you could see it generated a bunch of figures in here. So right now, this is the final figure that I'm showing here. I'll zoom in. And this is the parity plot. This is the ones on here are the actual values. Okay. And in here, it's the predictive values, and you can see how they align. And it's very easy for a neural network to fit a data like this. It's very simple tabular data. And it also generated a bunch of other stuff like the residuals. You could see the residuals. And the training loss, you could see it in here. It also generated all of the figures. You can have them here, okay? And by the way, you can ask it to generate a report. Like if you want to generate certain PDF or a markdown or any kind of report you're interested in, you could do that in here. If you want to change the plot, like remove the grid line, you could ask it, remove the grid line from here. Like for example, remove the grid line from the training loss curve, okay? And by the way, I'm using, because I'm on auto mode, most likely I'm using the simplest model, and it could do all of this. So this is amazing. So I'm gonna click run, and it should be running, and it's asking me, see that? This is what it changed. So I can click on the change in here, and I can see what it did. So when I click on it, I see what it changed, okay? So it removed one line, and it added another line. So we have the plot dot grid. It was true, and it removed that. So the grid lines were there, and it just removed them, and it commented that I removed it per request. Okay, so I can click keep. Okay, and that's it. Depending on the model, if you're most likely having a smarter model than what I have right now here, it should run automatically again. So run the code again. Again, it should be doing this on its own. It depends, okay? Sometimes it acts up, but you could just ask it to run the code again. Or, by the way, you can execute the code yourself as well, okay? Like if you want to run it directly from a terminal, like you can have a terminal and run it here from the terminal. But again, I'm not here to teach you coding. We're more vibe coding in here. So click enter, allow. You see, it's very simple code, right? It's just running the code that I have in here. So now it's running, and now it's showing me the steps, and you can see how right now it removed the grid line. So what I showed you so far is what we call vibe coding, where you tell the agent to do everything for you. But let's say you want more control, which I think is a better way to do it. You can specify in a comment, in a Python comment, like you see the comments in here, and it will suggest things below, and it will, you could say like, okay, autocomplete it, okay? So it's more like the one you have on your iPhone, like the autocomplete. So it will understand what you're trying to do, and it will autocomplete, and it will suggest it, and it's up to you to accept it or not accept it. I want to actually do that in an interesting way. So I want to close VS Code, and I'm going to open something similar, the same thing, same idea, and it's going to be called a Cursor. Okay, so Cursor is another tool similar. It's actually a fork of VS Code. So someone forked it, and they created Cursor. Okay, so we can click Cursor. It's the same way you can install it. It's called Cursor AI, and you can install it. You could do whatever I want to do right now here in VS Code, but I want to show you that whatever you worked on, you can just hop in and continue somewhere else. So don't be worried, like don't worry about like transitioning to another software. Whatever you do here is just a bunch of software that you could use anywhere. So I can click here on it, and let's say I go any, like let's pick any, like whatever we're trying to plot, let's say. Okay, in here, let's say I want to remove this line. Okay, so I can remove this line, and I'm gonna say write the title of the plot, and right now it's suggesting the part below, so I can just click tab and it will continue it and it will get the title, which is great. Another thing you could do is you could see these suggestions here, like Control L to chat or Control K to generate. So you can actually select whatever you want, and you can ask for a quick edit here. It will open a box here and you can edit directly, ask what edits you want for here. Or you can ask it, add it to chat. So you can click add to chat and it will reference, it will know where you're highlighting, okay? So it will know what you're like trying. The thing is, like these LLMs usually will read a lot of your workspace, but it's a good idea if you need specific changes and you want to add it to the chat, you can add it also to the chat, okay? And Cursor or any other tools, usually they have, just like VS Code, they have multiple agents modes as well. So I hope this makes sense how we're trying to use. You could use this for machine learning, especially for machine learning to build models. And it will be very nice because you could not only generate something, you could generate figures, not just write the code. You can generate figures, debug all of them, and then also generate nice reports if you want. And as usual, please be cautious when you're using these tools because they can hallucinate and make up things. So yeah, just be careful. I want to just share a small story. One time I was trying to vibe code a neural network, and I asked it to write a code for a convolutional neural network, a CNN. What it did is it pretended it's generating a CNN, but in reality it just implemented an FNN, even though it called it a CNN. So you need to be very cautious. They're very good at tricking people that don't know how to read code. So be careful. Read the code. It's a good idea to practice reading the code and understanding. You don't need to write everything from scratch anymore. The tab method I just showed you is the best way to go right now. The final step in this course is to build something. The capstone is open-ended. Choose the track that best fits your interest. Track 1, for example, tabular prediction. Predict an engineering quantity from measured or simulated features. Track 2, symbolic regression. Recover or approximate a physical law from noisy data, then simplify the results for parsimony. Track 3, image-based inspection. Train a CNN or fine-tune a pre-trained model or other kind of models on an inspection dataset. Use metrics that reflect the cost of missing detections. Track 4, surrogate and optimization. Train a surrogate model like a CNN or whatever model you're interested in for an expensive simulation. Then use it to explore design trade-offs. As a minimum delivery for this project, please have a one-page problem statement, a dataset card, at least one simple baseline compared with a stronger model, an error analysis, a reproducible script, or a notebook, and a short report explaining what you built, what worked, what did not, and what you would do next. To close this course, machine learning is a tool, like finite element analysis or computation fluid dynamics. It does not replace engineering judgment, it extends it. You now have the vocabulary, the workflow, and hands-on experience to start applying machine learning to a real engineering problem. Now go build something real.